So good evening, all of you. Good evening, everyone. So first, check the voice and video clearance first. All of you clear? Okay, right. Okay, enough. Yes, yes. Anybody from last year? Last year students, just raise your hands. Yes, Pragati. Okay, right. Mm. See, I don't give much introduction about me because that is not that much importance. So first, myself, Khadar Basha. So working in AC Engineering Academy from 8 years, taking electrical machines. Okay. Yes. Okay. Okay. So total electrical machines, we have four parts in that. Transformers is what one of the part. And if you talk about the weightage of these transformers for gate or engineering services, anything. So weightage wise, whatever the four parts we have, what are the four parts we have? Transformers, induction machines, induction machine, DC machine, and synchronous machine. So the four parts are having equal weightage with respect to written test. So if you go to any competitive examination, you will see questions in the four parts. We cannot say that transformers is most important or synchronous is most important or DC is very less important like this. For written test point of view, all the four are having equal weightage. So you should not neglect any part here. But I can say the weightage is different in the interviews. For any interviews, that may be any PSU interviews or engineering services, or if you attend any type of technical interviews, the weightage will be changed at that time. And in the interview point, the maximum weightage or mostly the weightage is for transformers, induction, synchronous, and DC will have a little less weightage there. DC machine, because if you observe in our regular life also, what is the application of DC motors or generators? Very less. So if you observe in your domestic purpose in your home or nearby, do you have anywhere DC motors? Very less applications we have, because for DC motor you need DC supply. Is it available readily? No. So most of the motors for domestic purpose we are using are what? Induction motors only. Okay. That's why the weightage will change in the interviews, but not in written test. Okay. And for your doubts, you can contact to this number. Only in the Telegram it will work. So please note down this. This is for Telegram only. Don't send each and every small questions or small doubts also there. Whatever it is important, send that is on. Okay. Only for Telegram it will work, not for WhatsApp. Now let's see the weightage of transformers in the previous years in the gate and engineering services. This is the weightage of transformers in the previous years. So on an average, from total electrical machines, if you talk first, total machines, all the four, if you talk, so we are getting on an average 10 to 12 marks every year in the gate examination. It is 10 to 12 marks we are getting in the gate examination. Okay, from total machines. And in that, for transformers only, if you talk, 3 to 4 marks we can expect. So 3 to 4 marks we can expect from transformers for gate examination. Okay, this is up to 2020, and recently in 2021, from total electrical machines, we have 7 questions. Total 7 questions. In that, 4 are 2 marks and 3 are 1 mark. So totally 11 marks we got in the 2021 this year. Okay, so on an average 10 to 12 marks we can expect from total machines, and in the transformer approximately 3 to 4 marks we are getting. So after mathematics, the highest scoring subject means you can consider electrical machine. So don't leave electrical machines, and most of the people will feel difficulty in this subject, particularly mainly in the problem solving. So problem solving is very easy only when you know the concept behind every question. So reading question everyone will read, but who will understand the question? The question will be understand by the student who is having good information about that concept. Otherwise, understanding question itself very difficult. Okay, so electrical machines is not a difficult subject. I consider the most easiest subject in the total electrical engineering is machines only, no doubt in that. The most easiest subject it is, and easily we can score. If it is given for 12 marks also, guarantee you can score 10 marks in that if you just generally average prepare. And if you highly prepared, then definitely you can answer all the questions. 10 to 12 marks you will get. But only with our classwork, if you are perfect, you can score easily 10 marks. Only with classwork, no additional work required. So only with classwork, you can answer easily 10 marks. Okay. And for engineering services in the prelims examination, it is. So we are not talking here about mains examination. So for prelims, if you consider only transformer, it is. For only transformers in the prelims, we are getting on an average 3 to 6 questions. 3 to 6 questions mostly every year we are getting. These are 3 to 6 questions. Okay. Like that, from total electrical machines, we are getting 25 to 30 questions. 25 to 30 questions we will get from total electrical machines. Okay. So this is regarding the weightage of transformers in gate and engineering services. Okay. Next, let's see in transformers what we are going to see and what is the syllabus. And mostly it is common for both gate and engineering services. And for engineering services, little extra theory we have to read, little, not much difference compared to gate and ESE. Almost same, 95% both are same. But some concepts like Scott connection we have, that is not there in gate examination, but we have in engineering services. That is like that, some connections we need to concentrate here for engineering services particularly. See this. So this is the transformer syllabus totally we have. So in the same sequence, we will go throughout the subject. Sequence is very important here. Sequence. So first we will see introduction. So directly we cannot see voltage regulation, or directly we cannot see efficiency of transformer. To see about voltage regulation, suppose you need the concept behind that particular topic. So for that reason, we will follow the same sequence, whatever the sequence we have. So note down, it is same sequence we follow. And small suggestion is, so mostly every day, whatever the PDF, whatever the class is going on, that PDF will be uploaded to you. But the best thing always is our own handwriting notes. So don't say consider that PDF will be available, we can read from PDF. Yes, PDF is secondary, not primary. Just keep it is as backup, but not it is your primary notes. Not only for this, for every subject, it is better always to have a own handwriting notes, your own handwriting notes. That is the best notes always. Okay, PDF will be there, but don't consider it is itself the main notes. So take down this. First we will see introduction of transformer. First we will see introduction of transformer. Here we will see about definition of transformers and features of transformers. Okay, and different types of EMFs we have, and what are the types of that EMF we will see in this introduction part. And Faraday's law we will see here, and about Lenz law, and also about finally dot convention, how to place dots in the primary and secondary windings of a transformer. That we will see completely in introduction part. Okay, and then we go to construction of transformer. Once you know about construction of transformer, what is the next step? Operation. Now we will operate the transformer. Now when you operate, you will get some losses there. In the next step, once you operate, next step we will know what are the losses first. We will know what are the losses present, and then first we will see losses, and then we will conduct tests on transformer to find that losses. First, we will see what are the losses in transformer. Then we will conduct tests on that to find the same losses. Now, once you know losses, what is the next step we have to do? Performance. So once you know the losses, then we go to performance of transformer. Two performance parameters we have. One is voltage regulation and other is efficiency. So these two we will cover in this performance parameters of transformer. Now, after completion of this, here itself we see some important topic like non-linearity of transformer. So there is a non-linearity behavior due to magnetic material, that is core of transformer. We will see the non-linearity of transformer after completion of performance here itself. Okay, with this single phase transformers will be completed. Up to here single phase transformer only. Up to here single phase transformers only we will see. And after that we start here three phase transformer. Okay, three phase. So in the three phase transformers, again we have many subtopics. Just these are main headings, but many subtopics will be there in each and every heading here. In three phase transformers, you will see again the special transformer connections like open delta connection or Scott connection, and delta zigzag star connection, and star zigzag star connection. So these are all will come in the three phase transformers itself. Okay, these are special connections. And finally we complete the transformers with this parallel operation and auto transformers. Okay, finally we will consider this parallel operation of transformer, and final topic is auto transformers. Now if you talk about out of all these, which is the most important for GATE? For engineering services, I cannot say this is most important. For engineering services, I cannot say that this topic is most important, this is most important. For engineering services, each and every line in your notes, you should be fulfilled. You should completely learn each and every point. I cannot say this is only the most important, but for GATE point of view, I can say that is the first preference I go every time is losses. So last year also I said, in the losses, definitely 99% you can expect one question from this. Now in GATE 21 also, there is a 2 marks question in the losses. There is a 2 marks question in the losses directly. Very easy question, whatever we have solved in our actual classwork, same model question we got, and that question also on iron loss. In the losses, only the question possible is from iron loss only. Losses are, we have so many types like iron loss, copper loss, and stray load loss, and dielectric loss. Out of all, iron loss only the most important, and remaining you can neglect. So first preference is losses. You can expect one question from this. And next one is operation of transformer. So here you will get some other subtopics like EMF equation and all. So that EMF equation related problems important. So this is important first, losses, and next preference is for operation of transformer. Okay, and next is performance parameters, and then auto transformers. So these four are the first choice to prepare before examination for gate point of view. Okay, very important. Regularly in these four topics we are getting questions, and then you can go to other topics like three-phase transformers, important. Like we can say like this for gate point of view, but we cannot say for engineering services. Engineering services, each and every point you should be perfect. Okay. See, three-phase, you should have some information. Three-phase transformer is very important because from which transformer you are getting supplied to your home? Is it single-phase transformer or three-phase transformer? Mostly 90% three-phase transformers only. Only in some rural areas or very low load applications, there they use single-phase transformer, but mostly three-phase only. Yes, harmonics, excitation, and that is all will come in the non-linearity topic. Yes, so this is enough. Whatever we are seeing here for GATE and ESC, that is, and this is enough for each and every examination, not only for JE and all. See, if you are perfect in GATE syllabus, no, then you can attempt any type of examination very easily. For particularly JE, some of you asking for junior engineers, can we attempt? Yes, because the level of questions in JE is very less compared to GATE examination. So once you are perfect in this course, you can attempt any type of examination. Yes. Vector groups also will come in three-phase transform. Vector groups that will come in three-phase transformer. Actually, regarding these vector groups, three-phase transformers, vector groups, it was in this year 2021. Particularly in this year, it is given particularly in the syllabus. Vector groups. Previously, it is not mentioned. In the previous years, it is not mentioned about vector groups. But in this year, GATE 21 from IIT Bombay, in the syllabus, they mentioned about vector groups particularly. First time it is. But still, we did not get any question on vector group this year. So maybe we can expect by next year or some other. Okay, vector groups we will see clearly in three-phase transformers. Yes, for yes, for assistant engineers are these are all very easy. So once you complete this GATE syllabus, no, you can answer any question for any examination very easily because GATE syllabus is enough for every examination. Okay, so this is we are going to see the syllabus of transformer particularly. Now let's see some textbooks. So what we have to read. So these are the standard books. You can go through these textbooks. So I think most of you in your engineering has engineering. Maybe you have gone through this Thereja, right? These textbooks mostly will prepare, or mostly the people will go through this Thereja textbooks. But from now onwards, you should not open or you should not touch these textbooks. This Thereja or small local authors never prefer because these books are good to have a small definition, a small type of questions. This is enough up to your engineering studies. But from now, for any competitive examination, particularly GATE or engineering services, anything, these books are not sufficient. You can go through that. So I'm not saying that don't, no, not at all go through that. You can go, but don't prefer first it is. Prefer first ES Bimra. The first preference is this one, PS Bimra. And after PS Bimra, you can go through Nagrath and Kothari. This is the second preference. First is PS Bimra and then Nagrath and Kothari. Okay, and one more, we have the foreign authorities, Fitzgerald, a good one, but maybe it is not available readily. You can download. Otherwise, if it is available with you, you can go through these ones. Okay, and one more we have series, Ashfaq Hussain or H. Cotton, Alexander or MG Say or JB Gupta. So most of you may be familiar with this JB Gupta. So JB Gupta is also good. So we have many types of questions in this example questions. You can go through this. So PS Bimra, Nagrath and Kothari and JB Gupta. So mostly these three are enough, but everyone cannot buy all these books. No. So my suggestion is for all of you, because uh, all topics are not good in one textbook. Like if you take PS Bimra, every topic whatever we are seeing here, it is not good in PS Bimra, are not good in Nagrath and Kothari, are not good in JB Gupta. Some topics are good in some books and some other topics are good in some other books. So like that we have. So it will take so much time, it will consume so much time of you. So these are all just wasting your time. So my first suggestion is, so go through our class notes first. If you are perfect in the only class notes from starting day to end of the day, if you are perfect in the notes, I am guarantee 90% of any competitive examination questions or anywhere, GATE or ESE, you can easily answer. No doubt in this. Okay. After completion of this class notes, after completion only, otherwise it is enough, because our syllabus itself so much. So we are very proud that, what proud is, electrical engineering students only will face so much syllabus. No other engineering people or graduates will have that much syllabus. Like if you compare electrical and EC, electronics and communication people, so almost EC and EE, electrical, both having almost same syllabus. What is additional to the EC people? Maybe some communication, and in the transmission line EMTL they have, and EDC. Just combinedly if you take that is also more, not more than 150 hours. But we have additionally electrical machines, power system, power electronics, measurements. So only our electrical machines will take nearly 150 to 200 hours. Now you can check how much syllabus we have when compared to other engineers. So as our syllabus itself is very vast, so my suggestion is first go through our class notes completely. 100% you should be perfect. After completion of class notes, then go to standard books. Anything, whatever available with you, maybe Bimra or Nagrath and Kothari or JB Gupta or anything. Okay. After completion of this only, you go to standard books. Then you can understand. Suppose if you take any PS Bimra, suppose, let us take PS Bimra and open any one page in transformer topic and try to read from starting to ending of that page with proper understanding. Can you understand? No. 10% also you cannot understand it. Guarantee it is. So at the first attempt, directly you cannot learn from that. You cannot learn from that. So my first suggestion is this. So be perfect in the class notes. Then after completion of this, if you read a little Bimra textbook, suppose, then you can understand 50% directly in that. 50% you can understand, but not completely again. It will take so much time. So these are all not required now. The best thing is complete our class notes perfectly first and solve the previous questions. So these are more than enough, because our syllabus itself very, very vast. So no need to go again so many books like this. So these are all just for reference. If you want any more example questions, then you can refer these books. Okay. Just note down these textbooks. For ESC also same. For AE, which book means? don't have any separate books for this. In for AE, you can refer our AS material, the previous questions we have and practice questions. You can go through that enough. And JB Gupta and PS Bimra, the objective type of questions also available. You can solve that enough. See, yes. So one of you asking about see, questions of machines are little big. Questions of machine looks very big. Sometimes big questions, sometimes small questions. Mostly, if question is very big, people what the people will do. So most of the people, if any question is bigger one or lengthy question, and just by observing the question, they will leave the question. But that is not the good thing. Why should we leave that question just by looking at the size of the question? No. So what we have to do is first we should know subject. If you know the subject and try to read that question, whatever the length of the question, with some patience. Okay. If you know subject, you can understand the question. Otherwise, if you cannot understand question, definitely you cannot solve. No doubt in that. Okay. So we will solve many questions here in the class itself. Many questions, previous questions or practice questions or example questions. Many questions we will solve. These are more than enough. A PDF will be there in the same day or next day. You will get a PDF of, suppose today class is completed, by tomorrow mostly you will get the PDF. So cutoff depends every year, so we cannot say exactly this is cutoff. Yes, Chapman also good one, but you go through for theory. Don't go to any textbook. For theory point of view, you no need to go any textbook first. Only for numerical point of view, if you want, you refer some textbooks enough. Yes, you can solve standard example questions from any textbook. You can solve. Okay. Yes, for gate also, if you solve the previous ESE questions, that is added advantage only. No, you can solve. Yes. Yes. So if you want to go any PSUs, no, definitely your rank must be below. For a good one, you should have below 200 or 300. Okay. For ONGC or HPCL like this, you should have below 200, 2 to 300. Okay. Yes, we will start. Yes, you try to read after completion of some topic, no transformers. Then you try to read Bimra. Then at least you will get understand it. Okay. So it will take 10 to 15 days. If you take like this, now daily 5 to 9, if you take, it will take 10 to 15 days. Yes, test series, whenever it starts, no, after completion of your syllabus mostly, then only you attempt test series. So right now there is privatization is not at all coming into picture. So no need to worry of that. Still so many opportunities we have through GATE. Yes. Okay. So we will start now. There are so many messages cannot be read. Okay. So first see some introduction of this transformer. What is the need of transformers for us? So what is the application of these transformers? In what way we are using transformers? And what is the need of these transformers? It's a very, very important device in complete electrical technology, that is uh, transmission side and distribution side. So complete distribution. In the distribution side, transformers are playing very, very vital role here. Now, what is the need of transformer? Yes, very, very important. Without transformer, suppose there is an alternator or generator. From the generator, can we take directly supply? Can we take directly supply? Yes, we can take, but there are so many problems. If you take directly from generator supplied directly, what is the power generation? We are generating in the voltage levels 11 kilovolts, okay, and some MVA capacity. That's some 100 MVA, 100 MVA, okay. These are line 3 phase. I'm considering 11 kV, 100 MVA capacity of generator it is. This is for generator I'm writing. Suppose there is no transformer, what happened I will tell first. So a generator produces voltage of 11 kilovolts and capacity is 100 MVA. Now, if you calculate from this the current rating, so volt ampere means what? Voltage current product. Voltage rating is there 11, then you can find easily. So as it is 3 phase, 100 into 10 power 6 divided by root 3 into line voltage. What is line voltage? 11 into 10. So if you calculate, you will get some value. Okay, calculate this, you will get some value. Now this magnitude of current is very high. It is, this magnitude of current is very high. Some thousands of amps you get, suppose some thousands ampere you are getting. Now whenever current rating increases, no, generally where we have generating plants. So is the power plant is there beside your houses or homes or nearby your homes? Generating plants we have? No. Generating plants should locate far away from the domestic applications, okay, due to pollution of that everything. So it is far away from the consumers. Now let us consider after 100 kilometers away this generator is there. Now 100 kilometers you need to transmit power from generator to consumers. Now when you are transferring 100 kilometers distance, so much distance it is. Now you need to put conductors or not? Yes, three lines, suppose 3 transmission lines or 3 conductors you need to place from generator to consumers. 100 kilometers it is. Now what is the current rating we got here? Very, very high, thousands of amps we got. Now whenever current rating increase, then what should be the size of conductor required? Size. The size of conductor, size means area, cross-sectional area of conductor, is always proportional to magnitude of current. If current is small, you can use a thin wire. If current is high, you should use thick wire. In your home also you can observe that. For AC we use thick wire, and for normal fans we use thin wire, because current rating is more for AC. So like that, whenever current carrying capacity increase, the cross-sectional area should increase. Then what is the size of conductor? Increases. Now, as it is thousands of ampere, size of conductor is very, very big size. Then what is the weight of that conductor? Increase. So weight increases, cost increases. At the same time, how these lines, who will hold these lines? Towers, these transmission towers. So these transmission towers will hold. Okay. Then as weight of conductor is very big, as weight of conductor is very big, as weight is more, then in order to hold between two towers, that length of the wire, what should be the capacity of towers? It should increase or not? These towers should have very high capacity, because you you are using a conductor having very big size, having more weight for that, then tower capacity increases. Already conductor size increase, cost increase. Now tower capacity increase and maintenance also increase. Now overall your transmission cost increases very high. Then is it economical power generation? No, this is not economical power generation, because transmission cost increases. So we don't consider directly this is. Because of this reason, now what we do is we will use a transformer after generator at the power plant itself. Suppose 11 kV is generated, 11 kV, 100 MVA capacity. Now what we do is we don't supply directly to consumers. Now here we will place one transformer. Which transformer? A step up transformer we use. Step up. 11 kV will be step up to some 132 kV, for example. Just example, some voltage, some 132 or 220 or 400, some voltage level, it is step up. So when you step up voltage, see in transformer, volt ampere rating is same on both the sides. Volt ampere rating, kVA rating of transformer is same for primary winding, secondary winding, both same. So here 11 kV means current rating will be high on this. Primary side current rating will be high. Now here voltage increases. Secondary side voltage is how much? 132. Then what is the current rating on secondary? Decreases. Volt ampere remains same. Primary side, secondary side, if you calculate VI product, that will be remains same. So capacity no change. Same capacity is there. Now what we did here, we are reducing current capacity. Magnitude of current capacity we reduce by using a step up transformer. Now what is the magnitude of current flowing in the lines after transformer? Small current. Current rating reduced, but voltage rating we increased. Okay, voltage rating increase. Now people will get doubt. When you increase voltage, then you should increase insulation. But what insulation? Where you are placing conductor? In the air itself. Here air itself insulating material, having some dielectric strength. So free of cost. So you no need to spend anything for insulating material here. Okay. 1 second. Okay, so when we step up the voltage, when we step up the voltage, the current rating is decreasing, so the magnitude of or size of conductor required also rates less. When size of conductor is reduced, when current reduce, size of conductor reduce. When size of conductor reduce, the cost of conductor automatically reduce, and transmission tower capacity we don't require that much. So these are all advantages. Now transmission cost is what reduces. Now once you transmit this high voltage, now 132 kV, now you are transmitting, suppose you are transmitting using transformer here 132 kV, but at the consumer or receiving end side, at the receiving end side, what is the voltage required for us? So for our domestic purpose, what is the voltages we are using? Low voltages, like 220 single phase, or three phase is for 440 or 400. So this is small voltages we are using. So again we need to use a transformer here, and this transformer is step down. That 132 kV we have to step down to the three phase voltages like 440 volts. So there we use step down again. Now like that, many transformers we use at the distribution side for different loads. So transformers are playing now very important role here. Generator generates power, transmission, distribution, everything is by transformers only. And finally at the domestic or consumers, we are using motors. So motors also playing very important role throughout world. If you consider, without motor nothing will work, nothing. Manufacturing and each and everything, domestic purpose, so many applications. Now if you consider ceiling fans, everything, and particularly now we have the technology of this uh, static devices, that is power electronics. So using this, if you consider in your home, the washing machine, what is the technology we are getting? Inverter technologies. Now ACs also we are getting inverter technologies. Previously we don't have all this. Now for the same motor they are using inverter technology. Inverter technology means simply they control with the DC power there. They control with the DC power. Controlling is easy with that, and they are using many this semiconductor devices like SCR to control, and they are calling it is inverter technology. So like that, motors are playing very important role finally at the consumers, and in between transmitting, distribution, transformer is playing a vital role. Now all of you clear what is the main advantage of these transformers? So at the transmission side, it is step up the voltage we are using for step up application, and again at the distribution side finally we are using step down transformers. Okay, clear all of you this? What is the use of transformers in power system? Yes. Yes, I will give notes on every topic most. See, just now I said, no, what is the use of step up here? Why we are stepping up the voltages? If you don't step up the voltage, what is the magnitude of current at that time? Very high. For 11 kV only, if you directly transmit with a 100 MVA capacity, current rating is very high. Then when current rating increase, what is the size of conductors increasing? When size increase, cost increase, maintenance increase. So overall transmission cost increases. So to reduce that, we are using a transformer which is step up. Now once you step up, then what is the magnitude of current there? Reducing. Voltage is 132. Now current rating will reduce. For same volt ampere capacity, for same power capacity, current rating reduce. When current rating is reduced, advantages, size reduce, overall transmission cost is reducing. Okay. Now at the distribution, yes. Yes. So based on, see, at the distribution, yes, good one. One of the student is asking, as we are using step down transformer, no, step down transformer we are using. But at the distribution side, we don't use single transformer. We use many transformers here in parallel, and power capacities will reduce. Same 100 MVA will not come to one transformer na here. Many transformers we have at the distribution, many transformers. That 100 MVA capacity, which is generated, that is distributed among suppose 100 transformers. Then automatically, whenever voltage is reduced, step down, don't consider that current is very, very high. Not very high. Current is limited here. Based on the capacity of transformers we are using, that current will be limited. Okay. In our states, we have step down only, not step up. So whatever the transformer you are getting supply, no, the transformer is mostly three-phase transformer, which is step down transformer of rating 11 kV by 440 volts. So from this transformer, mostly you will get supply 11 kV by 440, and 440 is three phase. Again, in that we are using only single phase now, one phase, one neutral. So there you will get only 220 or 230 volts, single phase. Okay. Voltage drop will be there, but we will compensate that small voltage drops. Don't compare with that because in transformer we will consider only volt ampere rating. We don't consider the resistance. No. No, no. Inverted AC means what? It won't run with inverter. Okay. Okay. So this is just introduction. What is the need of transformer for us? Now let's start the transformer. First, we will see the definition. Transformer. See here. So about transformer. So I think as electrical engineers, each and every student knows about transformer definition very well. So what is transformer? Immediately it will come. A static device which transfer power from one circuit to another circuit or one winding to other winding through magnetic path. Okay. So definition is simple, but here, particularly for interviews, if you attend, they will ask some particular point about transformer that you should be able to answer clearly. That is, so they never ask definition because each and everyone knows what is the use of that. But still, they will ask in some of the interviews at the starting. They will ask very very small questions. What is generator or what is motor? This is just to put you in the track. That means that they are asking a small easy questions to you just to put you in the track so that you should not fear of this interview. So they will ask first small questions, then they will increase step by step the level of questions. Okay. So first of all, in total electrical machines, whatever we have, except transformers, except transformers, that is, except transformers, we have generators, motors. That's it. So these generators and motors are purely energy conversion devices. These generators and motors are purely energy conversion device. So that's why we call electromechanical energy conversion devices. The generators and motors we call electromechanical energy conversion device. Means electrical to mechanical if it is a motor, or if it is a generator, mechanical energy is converted into electrical energy. So like that, they are called electromechanical energy conversion devices, generators and motors. But transformer is the only device in total machines. It won't convert any energy. Means externally, if you talk first, externally, what is the input to transformer? What is the input? The input applying to transformer is electrical power. And what is the output you are getting from transformer? The output also you are getting same electrical power. Is there any change in the form of energy? Electrical energy you are giving and same electrical energy you are taking from that. So there is no change in this. So transformer will not convert any energy first. Externally if you talk, but internally there is a magnetic energy. So first, this electric energy whatever we given is converted into magnetic energy, and this magnetic energy again converted into electric energy. There is an internal conversion here, no doubt, but there is no external conversion. But if you see generator, externally if you see, for generator what we give input? Mechanical input. And what you are getting from generator? Electrical. Mechanical to electrical. And in the motor what we are getting? We are giving electrical energy to motor, and we are getting mechanical energy from the motor, electrical to mechanical. So there is some form of energy conversion externally. And still in these generators and motors, there also we have magnetic energy. See, whether it is generator or whether it is motor, if it is generator, mechanical energy converted into electric energy. If it is motor, electrical energy is converted into mechanical energy. So if you observe, ultimately mechanical energy we are using mostly. So ultimately you are getting at the output mechanical energy only. Generator at the starting generations. For at the generations, what is the input of generator? Turbines, mechanical energy they are giving, and that is converted into electrical energy. And this electrical energy again finally we are using at the consumers, and finally that electrical energy mostly we are converting to mechanical energy in different forms, different ways, like in electrical vehicles also we are getting. So like that, in many ways finally we are getting mechanical application on. Okay, so what is the reason is electrical energy, if it is the medium, we can transmit and we can utilize it is in many forms. But mechanical energy, can you transfer? Suppose let us take 10 kilometers distance. Now from this point to this point, can you transfer mechanical energy in the easy way with a less cost? We can transfer 10 kilometers means we can transfer, but very, very difficult. You need bearing settings and gear settings, everything here. And so much big shaft is required. So it is very difficult to transfer mechanical energy, but easily we can transfer electrical energy. And this electrical energy you can convert into many other forms very easily. That's why electrical energy is very important here. And whatever it is, in between we have magnetic energy. Without this magnetic field in any device, nothing will convert. Without magnetic field, that may be transformers, that may be generators, that may be motors. If there is no magnetic field, you don't get anything from that device. It may be anything, generators, motors, transformers. Okay, so magnetic field is very, very important. Okay, so transformer is a electromagnetic energy conversion device, which is internal conversion only, but not external. Externally no conversion, electric only we are getting. Okay, first write the definition, then we will see about each and every point again in the diagram. Okay, so write the definition. What is definition of transformer? It is a static device which transfer power from one circuit to another circuit without change in frequency. That is important. Transformer will not change any frequency. Whatever you will give at the input, same frequency it will produce at output. Okay, write the definition first, all of you. It is a static device. It is a static device which transfer power from one circuit to another circuit without change in frequency. Without change in frequency. Which transfer power from one circuit to another circuit without change in frequency. So hence, like first point, it is called a constant frequency device. Constant frequency device. Transformer is constant frequency device. Yes. So small internet issue here. Okay, now all of you clear? Is it audible? Now all of you clear, no? Okay, right. Okay, right. Now see this. So it is called a constant frequency device. It is called a constant power device. Now it is called a constant flux device, and it is a 180-degree phase shift device. A 180-degree phase shift device. 180-degree phase shift device. So first take all the points, then we will see one by one. It is a 180-degree phase shift device. Next point. Next. It is a negatively feedback circuit. It is a negative feedback circuit. Negative feedback circuit. So these are all about regarding transformer only. Next, it is an electromagnetic energy conversion device. An electromagnetic energy conversion device. Next, it is a two-port network device. It is a two-port network device. It is a two-port network device. So these are the important points regarding transformer. So taken all of this. Now let's see one by one. Now consider a transformer. So we are applying an alternating voltage signal. Let some voltage V1 primary or input voltage. Now this is the signal we are applying. Voltage signal is this. Let this is the voltage signal we are applying to transformer, alternating, having some frequency f. This is V1, voltage signal V1, frequency is f. Let 50 hertz it is. Okay. Now once you give, or once you applied a voltage, a current will flow or not? Yes, definitely, because there is a path for current, closed path. Now a current will flow. Let it is a current I1, primary current or input current. Now what is the shape of that current? That is also sinusoidal, because voltage signal is what? Sinusoidal or alternating. So current also alternating nature. First of all, what is the nature of these windings in any machine? If you take any machine, transformer, static device, or rotating machines anywhere, like generators, motors, what is the nature of windings? Nature of windings means inductive or capacitive. Definitely inductive. Why? We use like a coil, no? It is. If it is a transformer, number of windings, number of turns we place at one, on one core or one limb, or at one place. Number of turns we are placing at one place. So it is like a coil or inductor. Okay. So the nature of these windings is mainly inductive. Ideal case purely inductive, but practical case not purely inductive. Some resistance also will be there, RL nature. Now considering ideal case, what is the nature of this winding? Inductive. So voltage signal started from, let 0 degree. Now where is the current signal? So we know, so you should know all these terminology from basics. So maybe everyone knows that in a inductor, what is the current always? Inductor current lags the voltage, and in a capacitor current leads the voltage. So this is the voltage signal taken from 0 reference. Now current signal will be after 90 degrees with respect to voltage. Current lags voltage by 90 degrees. So this is the shape of current starts from 90 degrees, so signal is shifted by 90. This is the current I1. Okay. So why we take a 90 degree? Because of inductive nature of this winding, current is shifted by 90 degrees. Okay, magnitudes may be different, voltage current magnitude not same, that is different. So we are drawing only signals, and whatever the frequency this voltage is having, this current also will have the same frequency. Frequency will not disturb, signal is just shifted. Okay. Now signal is just shifted by 90. Now what happened? Tell me here. Current is flowing. Current. This is the path of current. Now by applying right hand thumb rule, so we will see again the what is right hand thumb rule. Some basics. Now I don't give you here all the basics of machines. Only for transformer, whatever is required, that I will provide here. That is, for rotating machines, you need about mainly Fleming's rules, right hand rule, left hand rule, very well to understand the concept. But here that much is not required. If required, I will give at one place about Fleming's right hand or left hand rule, that is. Okay, but I don't give complete information of these rotating machines here. Now, by applying right hand thumb rule, so we will see again what is this. Just I'm applying. What is right hand thumb rule? If the thumb finger indicates direction of current, the remaining 4 fingers indicates direction of flux. In the same way, if the 4 fingers indicates current direction, then the thumb finger indicates flux direction. Vice versa it is. No, that is I am applying. So according to the right hand thumb rule, this current direction is indicated by our 4 fingers. Now thumb indicates flux. Therefore, the flux is coming in the upward direction. This is the direction of flux. Now same flux will take the path, as it is a closed path. Throughout the core, it will pass like this. This is the path of flux. Flux is passing in this direction. Okay, path of flux. Now, what is the nature of that flux? Alternating only, no? Yes, voltage signal is alternating, current flowing also alternating, time variable, that is alternating is sinusoidal, or you can say time variable current or flux. Now whatever flux produced here, that is also alternating flux. Now where is that flux with respect to signal representation? Where is that flux? Yes, the flux produced is also in phase with current. Remember this, wherever in the conductor the flux produced is always in phase with current only. Okay, this blue line is what? Current, and this black one is what? Flux. Magnitudes is different, but both are in phase. According to phasor relation, both are in phase always. flux produced always in phase with current, anywhere that is. Okay, this is the flux. Now, due to this flux, as this flux is alternating, a time variable flux, it is passing throughout the core or not? Yes. Now, it is linking with two windings, with primary winding and also with secondary winding. Same flux is linking with both coils or both windings. Now, an EMF will induce on primary, let E1. At the same time, EMF induced on secondary, let E2. Now, this E1 we call self-induced EMF, and we will see again what is that. And E2 we call mutual induced EMF. Okay, finally, EMF induced. EMF induced. Now, where is that EMF? If you draw these signals, voltage signal we drawn, and then current signal, and then flux signal. In the same way, if you draw the EMF signal, where it will be, that is also alternating, no doubt, that is also alternating, but where it is, that EMF signal, see, this is 0 degree, 90, next 180. Now this EMF signal will start from 180 degrees of some magnitude. That magnitude will depend on what? Number of turns here. So according to definition I'm writing, so clearly we will see again, this is E2. Okay, now why it is 90 degree again shifted with respect to flux? Where is the flux? Observe, flux is at 90 degrees. Voltage signal we applied at 0 reference. Then current lags voltage by 90 because of inductive nature of this winding. So 90 degrees shifted. Same frequency. Now this is 180. Flux also in phase with current. Now due to that flux, whatever EMF induced in the windings, E1 or E2, that EMF lags again by 90 degrees. Why it lags by 90 degrees? This is due to Faraday's law. This is due to Faraday's law. What is Faraday's law? According to Faraday's law, the EMF induced is what? A rate of change of flux. So EMF is always a rate of change of flux, d phi by dt. Okay, now consider here. In this signal, flux is sinusoidal now. Flux is sinusoidal. Now let us assume phi equal to some sine omega t, for example, sine omega t, sinusoidal variation. Now if you substitute here, what you will get in EMF? D by dt of sine omega t only, no? D by dt of sine omega t. Now if you differentiate here, what you will get? You will get sinusoidal only, but in the form of cosine terms. So now d by dt of sine omega t will be cos omega t into omega. Okay, like this. Now EMF signal is cosine. If flux signal is sine, EMF signal is becoming cosine signal. Now what is angle between sine and cosine? 90 degrees. That's why EMF lags flux by 90 degrees. Now observe, totally this is our input signal. This is our input signal. And this is our output signal. This is our output signal. We applied input voltage signal at 0 degree. But after how much angle we are getting output voltage signal? After 180 degrees, we are getting voltage signal. That's why we are calling this transformer, it is a 180 degree phase shift device. Now clear all of you why we call it is 180 degree phase shift. Phase shift means signal, how much angle the signal is shifted from one reference to other reference, input to output. Total 180 degrees it is shifting. Now I given clearly why it is 180 degree. So first current is 90 degree. So flux also same 90 degree. Then due to Faraday's law, whatever EMF induced, again it lags flux by 90 degrees. So total with respect to input signal, 180 degrees it is shifted. That's why we call 180 degree phase shift device. Okay. Now some people may get doubt, where is E1? How to draw that E1? E1 also in phase with E2. This is E2, no? This is E2. E1 also in phase with this. E1 also in phase, but magnitudes of E1, E2 different. Why? E1, E2 depends on number of turns. Primary turns N1 or secondary turns N2 here. Okay, based on the turns. Suppose N2 is more turns. Let us consider secondary having more number of turns. This is E2. Then E1 will be less than that. E1 is this. This is E2. Let this is E1. Just example I'm drawing. Both in phase only. E1, E2 both are in phase, but magnitudes are different. Why both are in phase? Because what is the reason for both EMF, E1 and E2? Flux only. Whatever the flux is passing, same flux is passing for both windings. Due to that, whatever EMF is induced, E1, E2, both are in phase only. And magnitudes are different. Why? It depends on number of turns. Clear all of you this? Lenz law is there. Still, we did not discuss. We will discuss about Lenz law separately. See, so why angle between sine and cosine 90? Sine and cosine 90. What is cos 90 minus omega t? Or what is cos omega t minus 90? Sine omega t only, no? Yes. Angle between sine function, cosine function always 90 degrees. Now clear? Now see, first we applied a voltage signal to transformer V1. To the input side or primary side, we applied a voltage signal V1. So this is the voltage signal we consider. So this is where it is started. We considered 0 degree. 0 degree it started. Now a current I1 is flowing. A current I1 is flowing, as the nature of this winding is inductive nature, because coiled. Number of turns, if you wound like this, it will become a coil. Now what, as it is inductive nature, current lags voltage always by 90 degrees in inductors. That's why I taken after 90 degrees current is started. I1 is started. Now once there is a current, flux will produce or not? Yes, that is by applying right hand thumb rule. By applying right hand thumb rule, a flux will produce. Now that flux produced always in phase with current. That's why I drawn this flux also in phase with current. Okay, the flux is also in phase with current. Now due to that alternating nature of flux, as it is connecting with both windings, EMF will induce in both windings according to Faraday's law, that is E1, E2. Now we are considering always secondary side only, no? Which voltage you will take outside or you will connect to the load? Secondary only we connect. That's why I'm drawing E2 first. That EMF induced in the windings lags the corresponding flux by 90 degrees. That is due to Faraday's law. Why it is, I explained here. Okay. So voltage signal we applied at 0 degree, but the voltage, output voltage from transformer we are getting after 180 degrees. After 180 degrees or after 10 milliseconds, if you consider in terms of frequency. Now observe from input to output. Is there any change in the frequency of any signal? This is F, 50 hertz input. Current also same, 50 hertz. Flux also same, 50 hertz. And EMF induced also same frequency will come, 50 hertz. So no change in frequency you will get. Whatever you applied on primary, same frequency signal you will get on secondary side. Due to this reason, we call transformer a constant frequency device. Yes, input also there. EMF induced in windings always 180 degree shifted. That may be primary side E1 or secondary side E2, anything. EMF angle between voltage signal applied and EMF induced in winding is 180 degree phase shift. Okay, that may be primary side or secondary side. We are considering mainly secondary side because that is only we are connecting to the loads, no? Not primary winding directly again. So what is the first point here? It is a constant frequency device. Now clear why it is called constant frequency? Because from input to output signal, frequency is not disturbed, only the signal is shifted by total 180 degrees, but no change in frequency. That's why we call constant frequency device. Next, second point. What is the second point? It is a constant power device. Which power it is? People will get doubt here. Constant power means power is having three types: apparent power, active power, reactive power. And this power is belongs to apparent power or complex power. This is apparent power. We are not talking about active or reactive power here, only apparent power, because rating of transformer is in volt ampere only. That is apparent power. So this is VI product. Okay. So we are talking about apparent power here. It is a constant power device. See why it is called constant power is observed here. If we consider in any transformer, let the primary voltage rating is some E1 and current rating is I1, and secondary voltage rating is E2 and secondary current is I2. Okay. Transformers may be two types mainly, step up or step down, or 1:1 also we have. 1:1 also we call isolation transformers. Main purpose is what? To either to step up the voltages or to step down the voltages. Now if you consider step down application, observe this. If you consider step down means primary voltage is greater than secondary voltage. Step down it is. So during the same time, current ratings will be reverse. E1 greater than E2, no? Then automatically I1 will be less than I2. So if you take any transformer, they will give some voltage rate, power rating there, 10 kVA, 20 kVA, or 1 MVA like this. And if you calculate the product of that primary voltage and current and secondary voltage and current, it will be same on both the sides. If voltage is step down, current looks like step up. So how we are calling step down? How we call step down? If secondary voltage is less than primary voltage, it is step down. If secondary voltage is greater than primary voltage, is step up. So you know very well. And if you calculate the product of this primary voltage current and secondary voltage current, these two will be same. That's why transformer we call a constant power device. Which power it is? Complex power or apparent power, not active power. Powers will never be same. If you take practical transformer, primary power, secondary power is not equal 100% practically. There will be some losses in that. And what is the equation? We know very well. Always input power is output power plus some losses. But in ideal case, we neglect that losses. Then input power equal to output power. Okay, ideal case only it is, but practically it is never equal. Slight differences will be there. But in all our calculations, numerical calculations, we will consider the primary volt ampere, secondary volt ampere, both are equal. Okay, we will neglect that small losses in this. This is we call constant power device. So almost constant, slight variation will be there practically. This is our second point, a constant power device. Primary volt ampere, secondary volt ampere is same in transformer. Okay. Next, third point is it is a constant flux device. It is a constant flux device. This point now itself we cannot understand. So I cannot show you also here. Now this point I will show you in the operation of transformer. Up to that you should remember this. Okay. There we will see how it is called constant flux device. Important question it is. Transformer is a constant flux device. We will see there. Remember this point. Next, fourth one is it is a 180-degree phase shift device. Just now we have seen why we call 180-degree. From input signal to output signal, there is a 180-degree difference. The output signal is shifted by 180 degrees. That's why we call 180-degree phase shift device. Okay, it is also clear. Next, fifth one is it is a negative feedback circuit. So this is many times in interviews also asked. In written test, mostly they don't ask this type of questions directly from definition point. But in interview, many times, many people faced this point. Transformer is what type of feedback circuit? Negative. Then they will ask, where is the feedback in transformer? Show you feedback in transformer. Can you show? Can you show feedback in transformer? Feedback. First of all, what is meaning of feedback? Feedback. Generally in control system, we learn about feedbacks. Positive feedback, negative feedback. Feedback means what? A part of output is fed back or given to input again. That is feedback, or the effect of output on input we call feedback. Yes, yes, observed. So, okay, most of you saying flux is feedback. Okay, right only, but there is one terminology to say why we call it is feedback is, see, according to control system point of view, if you learn first. So we have a forward path transfer function, vector output, input, and some part of output is fed back to input through a feedback transfer function, let h of s, like this. Now here we have feedback based on the sign, positive or negative we call. Now what is the feedback? The effect of output on input is called feedback. Now it may be positive feedback or it may be negative feedback. Now if you remember from control system point of view, tell me what is the positive feedback means? Positive. If the angle between input signal and output signal is how much? 0 or 360 degrees. If the angle difference between input signal and output signal is 0 or 360 degrees, yes, yes, we call it is, yes, 0 or 360 we call positive feedback. And if the angle between input signal and output signal is, angle between input signal and output signal is 180 degrees, then we call it is negative feedback system. Okay, so you know very well from control system it is. Yes. Now, what is the angle between input signal and output signal in transformer we are getting? 180 degrees. So due to this reason, we considered it is a negative feedback. Now, first of all, where is feedback in transformer? Is it visible? So here in this diagram, if you observe in this block diagram, feedback visible. Or if there is no feedback, no, directly we draw like this. This is input, output. Okay, there is no feedback. So here feedback is visible for us. But in transformer, can you show in this diagram feedback is there? Feedback is there, but it is invisible for us. So don't say that flux is going from output to input. This is a feedback. No, it is not directly. So the feedback, the term feedback in transformer, the term feedback in transformer is due to Lenz's law. The term feedback in transformer is due to Lenz's law. What is Lenz's law? Generally, if you consider Lenz's law means effect oppose cause. What is effect here? EMF induced in the winding is effect. What is the cause here? What is the cause for that EMF? Flux. What is cause for flux? Current in the winding. What is cause for current in the winding? The voltage signal, the input voltage you apply. Without that voltage signal, anything will happen in the transformer? Nothing will happen. Suppose in the same diagram, just you remove this voltage signal, remove the voltage signal. Is there current? Is there flux? Or is there EMF? Nothing. So as we applied a voltage signal, current is flowing, flux developed, and that flux is causing EMF in windings. And that EMF or voltage we are using to the loads. So finally, the cause for the EMF is voltage signal you applied. So according to Lenz's law, EMF induced is our output voltage. Output it is. What is the cause for this finally? Input voltage we applied. So effect of output is there on input or not? Yes. What is output here? EMF induced. What is input here? The voltage signal we applied. So that EMF will opposing this voltage or not? Yes, it is opposing. How it is opposing and all, now you cannot understand clearly. That you will understand in the operation of transformer. How this EMF will oppose the supply voltage. So there you will see clearly it is. Okay. So this is effect and this is the cause, input voltage. Now effect of output on input is there, but it is invisible for us. There is no physical path from secondary to primary like control system block diagrams. That's why the feedback in transformer, the feedback in transformer is an imaginary. are also called virtual it is. Means not visible it is. It is not visible for us, but it is there in transformer. And what type of feedback is there? Negative. Why we call negative? Because the angle between that input signal and output signal is 180 degrees. That's why we call negative feedback. Okay, this feedback is due to Lenz law. So if you get any question why we call, why, how there is a feedback in transformer, means this is due to Lenz law, which states that Lenz law we will see again clearly. Okay, next, sixth one is, it is an electromagnetic energy conversion. So remember, this conversion is internal conversion. You should mention it is a internal conversion, not external. Externally there is no form of energy conversion. It is a internal conversion, and it is called a two-port network device. Two-port network. So however, in network theory you have two-port networks, input port having two terminals and output port having two terminals. In the same way transformer circuit also looks. That's why we referred it is as a two-port network device, transformer. Okay, so all these points is regarding transformers. So if you face any, if you face this question in any interview, don't say only this definition from here to here. Everyone will say this, but where is the difference in you? It is a static device which transfer power from one circuit to another circuit without change in frequency. Everyone will say this. So say all the remaining points so that some importance you will get, like 180-degree phase shift and negative feedback circuit. You should be able to explain there, and how it is constant flux device. So this is we will see in the load operation. Okay. Hmm. Voltage or EMF both are same, but here according to Faraday's law we are calling it is like a EMF, means voltage only, that is negative feedback. Why EMF E2 is high? So in the diagram I drawn E2 is high, E2 is greater than E1. Just example I taken that N2 is more turns, N2 is greater than N1. More turns, more voltage. Just an example I consider. Okay, E1 may be greater than E2. That depends on number of turns. Not always it is like this. Hmm. Okay, clear all of you definition? All of you clear? Now one more. Remember here, the transformer windings we considered as primary winding, secondary winding. Primary means many people will consider always left side is primary, right side is secondary. Is it right? No. Primary winding, maybe you can take right side also. Now what is primary winding means? Primary winding means wherever you give supply, wherever you give supply to the transformer having two windings. Any side you can give supply, no? Any side you can give supply based on your requirement, whether you want step up transformer or step down transformer application, wherever you can give supply, primary and secondary. Now other way of representing transformer is what? Transformers we represent like LV winding, HV winding. Let LV winding indicating with less number of turns, HV winding indicating with more number of turns. Let it is LV winding, HV winding. So we can also call transformers as LV and HV windings. LV means wherever we have less number of turns, and more number of turns, high voltage winding. Now whenever voltage is less, whenever voltage is less, what is the corresponding current in this winding? Product of volt ampere is same. Volt ampere on both sides is same, no? So if voltage is low, automatically current rating will be more on this. And high voltage side, What is the magnitude of current? Less. Product of voltage current is same. Okay. Now, one important question. What is the relation between resistance of LV winding and HV winding? What is the relation? Both are same or having different? If it is different, what is the relation? Tell me. What is the relation between resistance of LV winding and HV winding? Let it is A, B, C. Tell which one is right? Relation between resistance of LV winding and HV winding. Which one is correct? Okay, good. Yes, most of you right. Most of you correct. Yes, enough, enough. Yes, most of you correct. The answer is C. Resistance of LV is less than resistance of HV winding always. So you should know this. In some of the topics, I don't write there. This is LV winding. This is HV winding. Just with the diagram, you should understand. This is LV winding. This is HV winding. So how we represent is observe. Generally, this low voltage winding. Observe. Low voltage winding. What is the rating of current rating here? High current. Low voltage means current rating will be more in this. High current will flow in this. As current rating is high or high currents are flowing in this, what should be the thickness of wire required? Thick required or thin required? Definitely thick wire required. So it should have more cross sectional area. See, I equal to V by R, and this resistance is what? Inversely proportional to resistance means resistance is rho L by A. So overall, R equal to rho L by A. Rho L by A. So this A will come to numerator. So current is always proportional to cross-sectional area of conductor. If cross-sectional area is more current can flow in this. Otherwise, if you take small thin wire for large current, it will burn. Okay. So high current, thick wire. It is made up of thick wire. Thick. As it is thick, what is the resistance? R equal to rho L by A. As area of cross section is more, automatic resistance will be less for this. So thick wire means resistance will reduce. Thick wire will have low resistance and thin wire will have high resistance. Now in the HV winding, what is the current rating? Less. So what is the thickness of wire we need to choose here? We need to choose less cross sectional area of conductor. Means thin wire is enough. Current is less, so thin wire is enough for us. As it is thin, automatically resistance will increase. Okay, high resistance. So resistance of HV is always greater than LV. Remember this, because generally some people will think here both are copper only. Both are copper, so both having same resistance. No, the thickness of windings will be different, little different for LV winding and HV winding. Both are not made up of same thickness. Materially same, copper only, but thickness is not same. So based on that, resistance will change. Okay. Yes, length of winding also. More turns means more length, no, automatically resistance will increase. Yes, right. Okay. So have some break. After break, we continue this. So take a break for 15 minutes and come back again. After that, we see some important one question on this definition itself, and then we go to the Faraday's law. Okay. Take break for 15 minutes. Okay, write one question here. If the transformer is supplied from, if the transformer is supplied from a square voltage signal, square voltage signal, then the shape of EMF induced in the winding is dash. Shape of EMF induced in the winding is dash. What is the answer? Yes. Okay. Its answer is here, square only. Answer is square wave. So you may get in the options also different types of signals. You have to identify what is the shape exactly. Okay. Answer is square only. Square. But a little change is there. Suppose, see, this is the voltage signal applied to transformer square. Previously, what is the signal we applied? Sinusoidal, alternating voltage signal. Now I am applying this voltage signal to the primary winding square of some magnitude. Let it is +1, -1, some magnitude. A square voltage signal is applied. Then what will be the shape of EMF induced in windings? Same shape. You can blindly remember this. Not only square. If they given, if triangular voltage signal is applied, what is the shape of EMF induced? Triangular only. Or if they given, if this voltage signal is applied, some random shape is applied, what is the EMF induced? The same shape. So whatever they given in the question, same is the answer, but what is the difference is, little difference is there. First, let us see here. This is voltage. This is the voltage signal we applied. Just like in our previous diagram, sinusoidal we apply. Now, when you apply square wave, what is the current? The current will become first. The shape of current here is, the shape of current will become triangular shape. The shape of current will become triangular. This is shape of current and also flux. Both are same shape, triangular only. Why triangular? And how to find the shape of current? Simple. Observe this. In the previous definition, we applied sinusoidal voltage signal and we got current also sinusoidal, flux also sinusoidal, and EMF also sinusoidal. So all are sinusoidal only. That is the beauty of this sinusoidal signal. For any other than sinusoid, if you apply, you don't get same all the shapes. Voltage, current, flux, EMF will not be same. They are different. Now, how to find that shapes? Simple. In a inductor, inductive nature, no, it is. Winding is what? Inductive nature. Then in an inductor, what is the voltage relation? In an inductor, voltage relation. Voltage V1 equal to inductance of that winding into rate of change of current, L di by dt. So in inductor, you should know that formula. So directly I'm writing, you should know this. What is voltage relation? L into di by dt. Now we need current signal. Then how to write current signal from this? I1 equal to 1 by L into integration of that voltage signal. So if you want current signal, you should integrate voltage signal. Then you get current signal. Now let this is voltage +1, -1, +1, -1, and so on. Now let us consider only this part. Considering only this from here to here, +1 magnitude is how much? +1 it is. Now if you substitute here 1 by L some magnitude, integration of what is, let it is 0, This is 1, for example. 0 to 1, what is the magnitude of voltage? Plus 1. So 1 into dt. Now 1 by L is some magnitude, and into 1 dt. What is integration of 1 t? Means ramp signal it is. So you will get a positive slope ramp. This is t. Like that, if you take 1 to 2, 0, 1, these two let 2 seconds. Now 1 to 2, if you consider, what is the magnitude? Minus 1. Then if you substitute here, minus t means negative ramp, decreasing. So like that, if you join all, you will get a triangular signal. Okay. So shape of current and flux is triangular. If voltage signal is square, if voltage signal applied is square, then shape of current and flux will become triangular shape because of integration of this voltage signal. Okay. Next, flux is triangular. Triangular means what? Combination of this ramp signal only. Now this is positive ramp, negative ramp, positive ramp, and so on. Now if you consider this positive ramp, what is EMF? How we get EMF? Rate of change of flux. In order to get EMF signal shape, you need to differentiate the flux. EMF is proportional to rate of change of flux, d phi by dt. Now flux is T, ramp signal. Now what is d by dt of T? D by dt of T, 1. D by dt of T. So generally we write minus n into d phi by dt completely. So proportionally I take it. Actually it is minus n d phi by dt. Then if you take completely, you will get some minus t. Let n equal to some 1 term, for example. Then it is minus t. Then if you draw minus t, minus 1 d by dt of minus 1, it is. What is differentiation of t? 1. So d by dt of d by dt means 1 minus 1. So minus 1. Again, if you take minus t here in the flux signal, minus t, minus minus will become plus, plus 1 you get, and so on. Now the shape of EMF, you will get the same shape whatever you applied the voltage signal. But what is the change? That 180-degree phase shifting will be there. Okay, signal will be inverted. Same voltage square signal will be inverted here. Same shape but inverted, 180-degree phase shift. So if in the option, if the waveforms are given, then you should identify square only, but which one is correct? Okay, you should identify. Now what is the shape of EMF? Square only. So you blindly remember whatever the voltage signal is applied. The EMF induced in winding is same shape. Now this is also one question in the previous one of the interview. They will ask this question first. You will say same answer, square. If square is applied, you will also say square. Then their question is again, why we are getting same shape here? Why we are getting same shape? If you apply sinusoidal, you are getting sinusoidal. If you apply triangular, you are getting triangular. What is the reason for this? Simple mathematical reason only. What is that reason? What is first mathematical expression we applied? Integration. First we integrated voltage signal. And what is next step we did here? Differentiation. So this integration and differentiation gets cancelled. From input to output, two mathematical expressions we applied. One is integration and then differentiation. So both inverted, no? So both get cancelled. Finally, same signal will come outside with a displacement. Clear? If you get any question, if triangular is applied or parabola is applied, what is the output we get? Same output is same parabola only. Okay, no change. Remember this point. Why minus 1? So actually minus EMF according to Faraday's law is what? Completely minus d phi by dt. Now we write complete equation. So proportionally and given rate of change of flux is nothing but EMF. But exact value if you want to calculate, this is minus n d phi by dt. So n is some number of turns. So I take an example 1 for small numerical. Otherwise, if it is 100 turns, minus 100. Minus 100 means some value magnitude compared to voltage signal. Okay, just example again. Clear all of this? Pratik, Nandan Kumaran. Clear? Yes, E1, E2 is due to flux only. EMF in the windings is due to flux only. Okay. Why it is same signal? Just now I said it is same we are getting because voltage signal first we integrated in order to get current. After integration we did differentiation. So both gets cancelled. Same we are getting. So make a note here, all of you. Note. Make a note regarding this. No, flux and current remain same always. Flux produced always in phase with current. Whatever the current, same is the flux. Flux equal to how I substituted is current I got 1 by L into T na here. Current is what? Function of T. Now flux is also what is flux? MMF by reluctance, N into I by reluctance. N will never change, reluctance will never change. Only current variation is there. That's why flux proportional to current. Whatever current is there, T, same I substituted. So just example I'm giving. You should understand this, okay? So make a note here. Note. The shape of EMF induced in the transformer windings. The shape of EMF induced in the transformer windings is always the shape of EMF induced in the transformer windings is always same as that of input voltage signal, is same as that of input voltage signal, is same as that of input voltage signal with 180-degree phase shifted, with 180-degree phase shifted. Okay. So this is on definition of transformer, one type of question. Okay, let's see now Faraday's law. Faraday's law. So everyone know very well about this law as electrical engineers. But question yourself once: have you did this law in your lab in your engineering? Have you did this test, Faraday's law test, in your lab? A small experiment. Have you did? Never. So I also never did. Frankly speaking, I also never did this small experiment. But everyone knows very well about this. But why we are unable to do? Yes, we are not doing that small experiments from where we can learn so much. This is the main drawback of electrical students. Everything we are trying to learn theoretically. Everything we are trying to learn theoretically, but not practically. Due to this reason only, it is very difficult to understand machines. But if you have a little good information regarding practicals, easily you can understand. So that you should be there in your engineering or colleges only, because once you come out from the colleges, we cannot do any experiment, no, practically. So during our engineering we never do all these practices. So we will go to labs, just for the sake of completing lab experiments, not to learn anything practically there. Okay, this small experiment we never did, and the people in the colleges also, they never show any interest to do such small type of experiments first. And we are doing many big tests like OC test, short circuit test, or DC machines, so many tests, synchronous machine, induction machine, block rotor test, no load test, many tests we do. But small experiment we never do in the lab. See, this is you can experience in your home also right now with a small little requirement. So I will tell. So first, what is Faraday's law? It states that whenever a conductor is placed in a magnetic field, and due to relative variation between them, an EMF will induce in conductor. And we have here mainly two variations. So I will tell clearly what is the two variations and what type of EMF we are getting in the machines. So first write the statement. Whenever, write the statement first. Whenever a conductor is placed, so in very small simple definition I will give, and I don't create big definitions here. Whenever a conductor is placed in a magnetic field, is placed in a magnetic field, and due to relative variation, and due to a relative variation, simultaneously write the nodes, and due to relative variation between conductor and flux, between conductor and flux, an EMF will induce, an EMF will induce in the conductor, an EMF will induce in the conductor. Okay. Now for this what we require? Mainly two things required: conductor required and field required. Enough. Now let us take a magnet. Consider a small magnet, right? North, south. Take a small magnet and field. So we know very well what is the field direction always? North to south. So north to south field is flowing. North to south. So field is there. Now we need conductor. So this conductor you can take any conducting material, maybe copper or aluminum, anything conducting you can take. So let us place a copper wire here. Or conductor is taken. So conductor is placed in magnetic field. Now EMF will induce or not? No. EMF will not induce. Why? You are not considering variation here. Now conductor is there, field is there, but one more is required. What is that? Relative variation. What is relative variation means? Relative variation means, suppose this is conductor, this is flux. Both are stationary. Then EMF will not induce. So according to Faraday's law, conductor should cut the flux lines or flux should cut the conductor. Any one variation should happen. If both are stationary, EMF will not induce, zero. So now let us rotate this conductor in the field. Let north pole, south pole. A conductor is placed, copper wire is placed. Now I will little rotate that wire between the two magnets, north and south. Now this conductor will cut the flux lines, then an EMF will induce. So that is Faraday's law. Now how can we execute this small experiment in our home? Yes, we can execute. We can do this experiment also. Now if you have small bar magnets, take north and south poles side by. Now take a small copper wire with loop. With loop means if you just take wire like this, and if you rotate also, you cannot identify EMF is induced or not. How can we know EMF induced? You should have some proof now EMF is induced. For that reason, what you can do is, let's connect a small LED to this. So this is copper wire, two ends. Now take a small LED. LED easily available in electronic shops. So bring that LED and connect a small LED here. Okay, take a small LED and connect to this, and hold the copper wire with any pliers, cutting pliers, not by hand directly. because if you hold also no problem, because as it is very small, you can hold, small currents only will flow there. So you can hold with a small nose plier, okay, cutting plier. Then make a small rotation quickly, not slowly. Slowly, if you rotate, you cannot identify that light LED will glow. That is, you cannot identify. For that reason, little quickly you have to rotate this. Then you can observe this LED will start little glow. So once LED little glow means Faraday's law is executed. LED is having some brightness means current is flowing. How current is flowing? EMF is induced. So directly you can say Faraday's law it is. So like that, at least we can execute a small experiment. Otherwise, in labs, generators we are operating. EMF is induced in generators. How we are calculating voltage in that? By connecting some voltmeters and all. But these are all not available for us right now. Like that, we can execute this. Okay. Now, mainly for Faraday's law, we required three things. One is conductor required, conductor. Second, field or flux is required. Third, a relative variation. So we have two variations here. Two variations. A relative space variation. First, write relative variation. Relative variation. These three things required. Suppose first one is there, second one is there, and relative variation is not there. Then EMF cannot be induced. So relative variation should be there. Now let's see what is the relative variation. Two types of relative variations we have. Let's see what is that. Relative variation. See, we have mainly two types. One is relative space variation. Relative space variation. Second is relative time variation. Relative time variation. Relative space variation, relative time variation. Now, simply you can remember relative space variation we have in generators. In DC generator and synchronous generator, we have relative space variation only. What is that relative space variation? In this variation, the flux, whatever flux we are using, that flux is time invariant flux. Time invariant flux means what? Time invariant. The flux will not change with time. Means what flux it is? Constant flux or DC flux. If you give DC voltage not to the winding, whatever flux is produced, that is constant flux, not variable flux. And that is a time invariant flux. But in relative time variation, the flux, whatever we are using, that is time variable flux, also called time variant flux. The flux is time variant, means what type of flux? AC, alternating flux it is. So in generators, DC generator or whether it is synchronous generator, we are using DC flux there. The flux is DC, constant flux, not variable. So in both DC generator and synchronous generator. Okay. And there the EMF induced we called dynamical induced EMF. Dynamically induced EMF. So what is dynamically induced EMF? The EMF induced in a generator due to time invariant flux. Flux is time invariant. Then which one should vary? Conductor should rotate. So if you remember in DC generator, flux is stationary, north and south, and armature is rotating. Conductor is rotating there. Now that rotating conductor will cut the flux line. So EMF induced. In synchronous generator also, if you remember, armature is in stator, winding is in stator. Armature means conductor here. That is in stator, and field is rotating. To that field we give DC supply, DC excitation we call. So clearly you will see in each machine. Okay. So totally in DC generator and synchronous generator, the nature of EMF induced is what? Dynamically induced EMF, where the nature of flux is time invariant flux. This is important. The nature of flux is time invariant, means DC flux. Okay, but in case of transformers, just now we have seen in definition also, what is the nature of flux in the core? Alternating flux, only flowing, alternating flux. So that is AC or time variant flux. And the nature of EMF induced we call statically induced EMF, because in this case conductor will never move. On the transformer core, is the windings are rotating or moving? No, windings are stationary, and only the flux is variable in that. Because of that reason, the EMF induced we call statically induced EMF. But in the generators, there is a conductor variation or flux variation. So that is we call dynamic variation. That's why EMF induced in conductor we call dynamically induced EMF. Okay. Any one, that is either DC generator or synchronous generator. Dynamically induced EMF. Only in transformer we have statical induced EMF. The nature of flux here is time variant. So if you see any question anywhere, if nature of flux in the machine is time invariant, then what is the nature of EMF induced? Dynamical induced EMF. If it is time invariant, definitely EMF is dynamical. If there is a time variant flux, means alternating flux. Time variant means what? Flux magnitude will change with time. It is alternating signal. There only it will change with time. There the EMF induced we call statical induced EMF. Okay. So right now we are not discussing anything about dynamical induced EMF, which is in generators only possible. So in transformers we have statically induced EMF. Okay. Let's see that statically induced EMF. That is DC flux. In the magnet, the natural magnets, whatever it is produced, the flux is what? DC, because poles will not interchange, no, always north and south only, same direction flux will pass. That is DC flux, time invariant flux. That is, if you want time variant, you should give alternating supply to a magnet, and their poles will interchange for every half cycle. That is time variable flux. From actual magnet, we are getting DC flux, permanent magnets. Okay. So dynamically induced EMF is possible with a time invariant flux. Statically induced EMF is possible with the time variant flux. So simply remember these 2 points. Now let's write statically induced EMF clearly. Right now, statically induced EMF. Statically induced EMF. So this is the EMF induced in the winding with a time variant flux or alternating flux. So considering a small iron magnet, iron bar, not magnet, iron bar, and on this we are placing two coils. So I'm placing two coils. Let coil 1 it is. This is coil 1 having number of turns N1, and one more coil I am placing on the same iron bar. Let coil 2 having number of turns N2 it is. Now we can say that these two coils are magnetically coupled. These two coils are magnetically coupled, means N1 N2 having same magnetic path or not? Yes. If flux is passing, same flux will pass for both coils. This is called magnetically coupled coils. Now out of these two coils, I will give supply to one of the coil. So I'm giving to the first coil alternating voltage supply V1. Okay, having some frequency F. Now, once I give voltage signal, a current will flow or not? Yes, a current I1 is flowing. See, here some important derivations will come, so observe carefully. So once we apply a voltage signal V1 to the coil 1 having number of turns N1, a current I1 is flowing, and this current also alternating only, no? Yes, this is also AC. Voltage signal is alternating, current also alternating. Okay, now this is the path of current. Current is flowing in the coil like this. Okay, now apply right hand thumb rule here for coil 1. Four fingers indicates current direction and thumb indicates flux direction. Now, in what direction flux is flowing? In this direction. This is direction of flux. By applying right hand thumb rule, if the four fingers indicates current, apply in your book, in your paper, then thumb indicates in this direction. Now, in the same direction, this flux will continue its path throughout the same iron core like this. Okay, this is the path of flux. The flux is passing in this direction, right? Same flux is passing for two coils. Now, an EMF will induce or not? Yes. Why? What is the nature of flux? AC, alternating. Current is alternating. Flux produced also alternating. Means for positive half cycle, see, this is north pole, this is south pole. And for negative half cycle, immediately it will become south and it will be north. So like that, the polarity of poles will interchange for every one half cycle. But we cannot indicate both the directions. No, that's why we take any one direction only. That's why I'm indicating arrows is like this. Okay, but flux will interchange for every half cycle. Then only EMF will induce here. Okay, now let us consider an EMF induced in coil 1 is E1, or we also call it is self-induced EMF. The EMF induced in coil 1 we call self-induced EMF, and EMF induced in coil 2 we call mutual induced EMF. Mutual induced EMF. Just like in previous definition, I indicated E1 in the primary, E2 in secondary. Now we are calling again specifically here self and mutual induced EMF because the statically induced EMF is two types. One is self-induced EMF. Self-induced EMF. Second, mutual induced EMF. Mutual induced EMF. Statically induced EMF is of two types. One is self-induced EMF and second mutual induced EMF. So take the figure all of you first. So before that, write one statement. Consider an iron core. Consider an iron core having two coils. Having two coils. Having two coils which are magnetically coupled, as shown in figure. Which are magnetically coupled as shown in figure. Complete the figure first. Induction generator also dynamically induced. Dynamical only, that is. Because their excitation we don't give, so you will see clearly in induction generator. Magnetically coupled means what? If two windings having same flux, that is called magnetically coupled. Just like mechanical coupling is what? Two motors, suppose two machines having same shaft connected, they are mechanically coupled. In the same way, two coils or two windings having same magnetic path or flux, same flux is passing through them. That is called magnetically coupled. Now let's see what is self-induced EMF definition and mutual induced EMF. Observe here, self-induced EMF first. See, it is the EMF induced in one coil. It is the EMF induced in one coil due to the time varying nature of current flowing in the same coil. So what is self-induced EMF? It is the EMF induced in one coil. Which coil that is? Coil 1. It is the EMF induced in one coil due to time varying nature of current, means alternating current flowing in the same coil. So wherever current is flowing, and in that whatever EMF induced, that is we call self-induced EMF. Now what is mutual induced EMF? Tell me now. Mutual induced EMF. It is the EMF induced in one coil. It is the EMF induced in one coil due to time varying nature of current flowing in another coil which is magnetically coupled. See, in the second coil, EMF is induced. It is induced due to what? The current flowing in another coil. It is EMF induced due to current flowing in another coil. And how this coil is connected to second coil? Magnetically coupled. Then only it is possible. Suppose if you don't magnetically couple, see there is one iron bar like this. There is one coil here. Okay, coil 1. And coil 2 I will place far away from this and in the air itself like this. Then do you get any EMF in this coil? Assume that this is so much distance far away. Definitely if you place far away, due to air which offers very high reluctance, flux cannot travel up to this coil. Then what is EMF induced in this coil? Zero. No EMF induced. So when there is magnetical coupling, then only maximum EMF induced is possible. Otherwise, if you place in air so much distance, EMF cannot induce because of high reluctance of the air. Okay. So write the two definitions. First, self-induced EMF. First one, put side heading, self-induced EMF. So here we get one important relation. So I think you should know this is from network point of view also. Still observe self-induced EMF. Write the definition first. The EMF induced in one coil. The EMF induced in one coil due to time varying nature of current. Time varying nature of current means alternating current simply. Time varying nature of current flowing in the same coil. Flowing in the same coil. Time varying nature of current flowing in the same coil is called self-induced EMF. Is called self-induced EMF. Okay. Now how to find this? This is from Faraday's law. So according to Faraday's law, EMF induced, because the nature of flux is time variable flux, which causes EMF in two windings. Not only two windings. If you place three windings, in three windings EMF will come. Then in the third coil also, whatever EMF induced, what we call that? Mutual induced EMF. And if you place fourth coil, what is the EMF induced? That is also mutual induced EMF. Now what is self-induced EMF? It is EMF induced in the same coil wherever current is flowing, and remaining all mutual induced EMF only if you place any number of coils. Okay. So example, just we taken two coils here. Now according to Faraday's law, we can find the self-induced EMF is, according to Faraday's law, minus n d phi by dt. N means how many turns are there in the first coil? N1. And rate of change of flux d phi by dt. So according to Faraday's law, EMF equation is written minus n1 d phi by dt. And this minus indicates according to Lenz's law. So we will see again after this what is Lenz's law clearly. So this is due to Lenz's law we placed minus n1 d phi by dt. Now the same equation we can also write like this, minus n1 d phi by di1 into di1 by dt. So what I did here, multiplied and divided with di1. See, both gets cancelled. Same equation. Same equation. Now I am considering this is as one part and this is di by dt. Now same equation I am writing as self-induced EMF equal to, this is I am considering as the self-inductance of the coil L. N phi by I. So in networks also, if you remember, what is the inductance formula? Phi by I for one turn, and for n number of turns, N phi by I. So it is also same, N phi by I. So L is this into di1 by dt. Because in any question, if you have inductance, you can directly use that inductance with the current relation. So that questions will come. So their inductance is there and current will be there. Then you have to use this equation. Otherwise, there are some questions. Number of turns will be available and flux signal or equation will be available. Then you have to use this equation. So based on the given data, you have to choose the equation. Okay, both are same. This is in terms of inductance. This is in terms of number of turns. Okay. Now observe here. There is one important relation with respect to the self-inductance L. Taken all of you up to this? Completed, no? That minus is due to Lenz's law. Minus is due to Lenz's law. We will see again Lenz's law. What is Lenz's law separately? Now observe. Therefore, L equal to, what is L? So magnitude I am taking, inductance magnitude. This is L. This is L inductance. N1 into d5 by di1. N1 into d5 by di1. Magnitude only I am writing. Minus I am not taking for this inductance calculation. Only magnitude. Now observe this. N1 into d by di1 of, what is the flux? How can we write flux? Flux. Observe in the first figure. Flux is produced due to, what is the flux equation? Tell me, in magnetic materials. MMF by reluctance. Flux is nothing but MMF upon reluctance. And what is MMF? Ampere turns, number of turns in that winding and current in the winding. N1 I1 by reluctance. Reluctance of the core material, iron. Okay, this is flux equation. Flux is due to I1 and that flux is passing for both coils. This is I am applying here. D by di1 flux N1 I1 by reluctance. Flux equation I written. Okay. Flux equation I written here just. Now this is N1. N1 is constant, no change. And reluctance also will not change, constant, into di1 by di1. So anyhow these two gets cancelled. So finally, what is the inductance? N1 square upon reluctance of the core. How to find self-inductance of the coil? The number of turns in the coil, square of the turns, number of turns by reluctance of the core material. Reluctance of the material. This is self-inductance of the coil. Okay. Now in the second case, we will find mutual inductance. In the same way, you will get mutual inductance. So after that, we write one important relation between two, self and mutual inductance. Clear? So this is about the first one, self-induced EMF. Let's see now second, mutual induced EMF. Second one, mutual induced EMF. So after this, I will give little information about magnetic materials also, because the terminology is required in transformers. Right. Second one, mutual induced EMF. Mutual induced EMF. Now, what is the definition of this? It is the EMF induced in one coil. That is what second coil, due to the time varying nature of current flowing in another coil. Which coil? Coil 1. And how these two coils magnetically coupled. So right there. It is the EMF induced in one coil. It is the EMF induced in one coil due to time varying nature of current, current flowing in another coil which is magnetically coupled, which is magnetically coupled, which is magnetically coupled. Clear? EMF induced in second coil. Why? Due to the alternating nature of current flowing in first coil, which is magnetically coupled. Then how to find this mutual induced EMF? Therefore, mutual induced EMF according to Faraday's law only, same, minus n d phi by dt, same formula we apply, minus n2, number of turns in second coil, no, n2, same flux is cos d phi by dt. Okay, now this is also I'm writing minus n2 d phi by di1 into di1 by dt, and people will get doubt why it is not di2 here. Why I'm not writing di2? Current flowing in first coil or second coil? First coil only current flowing, not in second coil. No, second coil is just open. That's why di1 by di1 multiplied and divided, no change. Now this term we call mutual inductance of the two coils. Now if we write mutual induced EMF equal to M into mutual inductance into di1 by dt. So if mutual inductance is there in the question, you can use directly this formula. If there is mutual inductance, use directly this. In gate 21, the question on this equation only. In gate 21, the question on this equation for 2 marks. Question is very easy, but most of the people got wrong while calculating this, because there is a slight twist given in the question. So that is also we will solve. Observe first. That mutual inductance M separately we need to calculate. Let's see. This is mutual inductance M calculation. Completed up to this. Okay, right. Now observe mutual inductance calculation. M equal to, what is M here? N2 into d phi by di1, magnitude. N2 d phi by di1. Now here also same, N2 into flux is due to first coil, no? So d by di1 of flux mmf by reluctance, N1 I1 by reluctance. Now N1 is constant, reluctance constant, take it is outside. Now it will N1 N2 by reluctance into di1 by di1 gets cancelled. So the mutual inductance directly we can find by this relation, N1 N2 by reluctance. This is M equation. Mutual inductance between two coils. Okay, what is self inductance? Same terms, N1 square by reluctance, and mutual inductance is combination of both N1 N2 by reluctance. Now make a note below these equations. Relation between self inductance and mutual inductance. We get one important relation. Observe this. Observe. Make a note. The self-inductance L equal to N1 square by reluctance, and mutual inductance M equal to N1 N2 by reluctance. Now observe these two equations. What is L by M? L by M. Reluctance gets cancelled. N1 N1 gets cancelled, and finally it is left with N1 by N2. N1 by N2. Now if you take reciprocal, M by L equal to N2 by N1. So in transformers terminology, what we call this ratio N2 by N1 as? We call this N2 by N1 as K, transformation ratio. So very well known it is. K is what? Transformation ratio. Important equation. Transformation ratio. Therefore, M equal to K times of L always. In some of the questions, they will give only self-inductance, but you need mutual inductance at that time. Then use the K. How to find K? K will be there from voltage rating given. Not only N2 by N1. N2 by N1 is also equal to E2 by E1. This voltage rating they will give in the question. Okay. Not only N2 by N1, E2 by E1 also you can choose. So important relation. Mutual inductance is K times of self-inductance. This is the first point in the note. Next, second point. Second one. So this is terminology related to magnetic materials. Magnetic materials. Just like electrical circuit, magnetic circuits we have. In electric circuit, current. Analogous to which one in magnetic circuits? Flux. So you know already all this terminology from networks. So in magnetic materials, mainly flux. What is flux equation? Phi equal to mmf upon reluctance. Okay, mmf by reluctance. Next, mmf. So if you write mmf only, what is mmf? mmf equal to ampere turns, number of turns and current. Ampere turns, number of turns and current. Next, magnetic field intensity. Magnetic field intensity. It is indicated by what? H. What is H? Magnetic field intensity, ampere turn per unit length. Ni by L. Ampere turn per length. This is magnetic field intensity. In the same way, what is magnetic flux density? Magnetic flux density. However, we have current density. In the same way, flux density. What is magnetic flux density? We write B equal to flux per unit area. Like current density, current per unit cross-sectional area. No? In the same way, flux density, flux per unit cross-sectional area of core. So this is one equation for flux density in terms of flux. And what is one more equation for flux density in terms of intensity? So if you remember these equations, mu h, okay, mu h, mu is what? Permeability, and h is field intensity. Same equation I'm writing. Taken. B equal to mu h, mu nothing but mu naught mu r into h, where mu naught is permeability of free space. Permeability of free space or air. And what is the value of mu naught? 4 pi into 10 power minus 7 Henry per meter. So units important. For engineering services, each and every point important. So don't neglect any point. Units of free space, permeability of free space is Henry per meter. And mu r is what? A relative permeability. A relative permeability. And for mu r, there is no units. No units for mu r. Okay. Mu r relative permeability. No units for this. So what is the relative permeability of different materials? In the magnetic materials, we have diamagnetic materials, diamagnetic, and we have paramagnetic, and we have ferromagnetic. So we use in all machines ferromagnetic materials only. In every machine, not only transformer and DC machine or synchronous or induction, everywhere ferromagnetic only. For diamagnetic, mu r is less than 1. The relative permeability is less than 1. And for paramagnetic, mu r is nearly 1, like 1.2 or 2 or 3, like that, very less. But for ferromagnetic, the mu r is very, very greater than 1. So generally for ferromagnetic in the range 900, 1000, 1100, 1200, in this range will be there for ferromagnetic materials. Very high permeability. The relative permeability is very, very high for ferromagnetic materials. So we always choose high permeability materials in every machine. Okay. That's why ferromagnetic materials only we use. Therefore, what is the B? Having two equations, flux per area and mu h. Now both I am equating here. So both I am equating. B is flux per area and mu naught mu r into h. Now from this, flux equal to mu naught mu r, h is what? Ni by L into A. Flux equal to mu naught mu r Ni by L into A. So totally it is mu permeability. You can also write total phi equal to mu into Ni by L, and this A also I am taking at the denominator. So let's write here phi equal to Ni divided by L divided by mu A. Okay, so we will get one standard form here. Observe it is. So previously we written directly what is the flux? MMF by reluctance. So this is MMF only, no? Ni means what? MMF. And here L by mu A we have. So this mu A completely I taken divided by L by mu A. So same value it is, same as previous equation, no change. So this is MMF by reluctance. Now you will get a formula of reluctance here. Very, very important calculation, particularly for engineering services in the prelims examination. You may get questions on calculation of reluctance of materials. Reluctance. So what is the formula of reluctance from this? L by mu A. Take all these points. See second point in the note. Related to magnetic materials, all these terminology. Flux, MMF, magnetic field intensity, ampere turn per meter. And this is Weber per meter square or Tesla. Weber per meter square or Tesla. Okay. Therefore, third point, reluctance. This calculation is important. Reluctance, let RL equal to L by mu into A. L by mu into A. Now, what is L here? This is important again. L. So don't say length of the core. It is not length of the core only. It is mean length of the core. So what is mean length? I will show you with example. Mean length of core. Next, mu, that is, permeability. Permeability. And what is A? Cross sectional area of core. Not area of core only. Cross sectional area it is. Cross sectional area of core. Okay. Cross sectional area of core. Now let's see one example how to find reluctance of this cores, transformer core. Mean length of the core, permeability of core, and cross sectional area of core. Now let's see small example. See example. Suppose there is a transformer core. So here mean length is not given, but length of outer square, inner square is given. See, so this is the length of outer square, 20 centimeters, and inner square length is given 16 centimeters. Now you need to find mean length of the core. Tell what is the mean length of the core. Mean length, L is how much? Tell answer for this. Outer square length is there, inner square length is there. One side is given. Then what is the mean length of the core? Yes, quickly. Mean length is how much? Mean length of the core is how much? So most of you giving wrong answer. I need the mean length of the core. That's why this calculation important. Yes. Yes, Anil right. Vamsi right. Okay, observe. Observe now. Enough. So mean length means don't tell only the length from here to here. Average length of this. Mean length or average length means don't tell only from here to here. From here to here length is how much? This is 18 centimeters, no doubt. This is 18. And what about complete length of the core required now? Flux is traveling throughout the core. So you have to find complete length of the core. That is mean length. Means this is 18 centimeter. This is also 18 centimeters. This is also 18 centimeters. This is also 18 centimeters. So all you should add total. Square core, all sides will be same length. So I given here outer 20 and this is 16 and this is 18 centimeters. Then mean length means this 18 into 4. 72 centimeters. Okay, this is the mean length of the core. Now in the same way, for example, I given a toroidal core or circular core. Suppose I given a circular core of radius 5 centimeters. 5 centimeters. Now what is the mean length of this core? Tell me. What is the mean length of this circular core? So there is a winding on this, like toroidal shape. There is a winding on this. Tell me what is the mean length. Flux is flowing. Whenever we excite, no, definitely current is flowing. Flux will produce and that flux will travel throughout the core. Now I need mean length of this. This mean length is required. Mean length. Mean length is nothing but what is the formula? Yes, 2 pi r, no? Yes, right. 2 pi r simply. Perimeter or circumference of this circle or perimeter. What is the perimeter formula? 2 pi r. 2 pi r. That is mean length for this circular core cross section, circular core. And 2 pi r equal to 2 pi into this radius, also mean radius, very important. Here I given directly mean radius, it is 5. Sometimes they will give the outer radius is some 6 centimeters and inner radius is some 3 centimeters. Then what is the mean radius? That you have to calculate and then you have to substitute in the formula. But here I given directly that mean radius r, so no problem, 2 pi into 5, whatever you get. This is the mean length of the core. Then you can find reluctance. What is the reluctance formula? L by mu A. So L we have, mu they will give, permeability of the core is how much? That is mu naught mu r they will give. And area, how to find area now, tell me? Area of cross section means this cross sectional area you have to calculate. And for that, again they should give in the question what is the radius of this. What is the radius? Let it is capital R, capital R, and this is smaller. Cross sectional radius it is. Then what is the radius of that circular cross section? Area of circular cross section, pi r square, no? Pi r square. So if you know the radius of this cross section, you can apply formula for that. Then you will get cross sectional area totally, pi r square. And what is the area of cross section for square? Area of cross section for square. Same, side square, no? So for that they will give what is the length of this side. What is the length? Suppose if they given each side length is a. So this is square. So I'm drawing cross section here like this. Each side is a. All are same a only. Then what is the area for square? If it is a, side square, whatever it is, a square. So like that, based on given type of core iron material, you have to find length and you have to find area for that. Then substitute in the reluctance formula, you will get reluctance. So particularly this type of questions mostly you will get in competitive examinations and in case of engineering services. But in the gate, very less chance we are getting the questions from calculation of reluctance. Okay. And there are one other model. So here I given a square core now. Now same square core, I will create air gap here. Let's see one more. Completed now up to this? Completed all of you? Okay, right. See, same square core I am giving again, but there I am creating a small air gap. Then how to find reluctance of this complete core? See, same square core, but a small gap is created. And the length of this air gap is given. The length of this air gap is, let L equal to air gap length is 5 centimeter. And the square side is, this is 20 centimeter, same as previous question. And the inner square length is 16 centimeter. And what is the mean length now? 18 centimeter. The mean length is 18 centimeters. Then if you want to find reluctance, how to find reluctance? See, the total reluctance, because when you place any winding here, and if it is excited with any supply, an alternating voltage source, current is flowing, a flux will produce, and this flux will pass throughout the core, through this gap also. Through this gap it will pass, but reluctance increase means magnitude of flux will reduce. So through this it is passing. through this it will pass. Now total reluctance offered to the flux we need to calculate. How to find? So here you need to calculate reluctance of core plus reluctance of air gap. So both you need to calculate separately, then substitute here. How to find reluctance of core? Reluctance of core. This is simple. Length of the core iron material divided by mu permeability into cross-sectional area of that core. Mu not mu r. So suppose iron is having relative permeability of let 1000. Relative permeability of iron is 1000 and relative permeability of air is what? 1. Mu r equal to 1 for air. Now you can substitute here. Length of the core. What is the length of the core? Tell me. From here to here 18 centimeters. From here to here this is 18 centimeters. In 18 centimeter 5 centimeter is air gap. Okay, 5 centimeter is air gap, means remaining 13 centimeter is core only. So here 18, here 18, and this is 18 and this is 13. So total how much? Length of the core 18 into 3 plus 13. This is length of the core divided by mu naught mu r. What is mu naught? 4 pi into 10 power minus 7 into mu r is given 1000. Length permeability of core is what? Permeability of core is 1000 and this is for air 1. So that is I substituted mu naught mu r into cross sectional area that we need to calculate based on the given data. So like this reluctance of core you will get. And how to find reluctance of, similarly, reluctance of air gap? Same formula, length of the air gap divided by mu a. Now length of air gap how much? 5 centimeters. 5 centimeters divided by mu naught is 4 pi into 10 power minus 7 into mu r is 1 for this into cross sectional area. And how to find that cross sectional area? So for this there is one more concept here called little. Here you should not take same cross sectional area. The cross sectional area little increases here. This is called bulging of flux. Flux will flow like this. Flux will flow like this in the air gap. So that cross section little increases. In the air gap, the whatever the flux is passing, that cross section little increase. This is called bulging effect. Bulging effect. So that you will see in magnetic materials clearly. Okay. So that area they will give in the question. In the air gap, the flux having cross sectional area that they will give in the question. So that you need to substitute and total reluctance you will get. Okay. So this is total reluctance of the core with combination of core and air gap both. Then you need to calculate flux, mmf by reluctance. So sometimes they will ask calculation of flux, or sometimes they will give flux, and in the mmf you will have current. They will ask current, how much current in the winding is required to create this much flux. Flux they will give, current you need to calculate. So different types of questions, but you should know procedure first, how to find that. Okay. Clear now, all of you? So these are the terms related to magnetic materials. Okay, let's see about Lenz law now. Lenz law. Lenz law. So Lenz law means everyone will say that effect oppose the cause. And what is the effect? How it is opposing the cause. So that is important to understand transformer action here. Okay, now see this. Now to understand, so again I will take the same figure for statical induced EMF, whatever I taken, two coils, same I will take. Observe. So considering again two coils, just like transformer only, it is primary, secondary, and here we are calling coil 1, coil 2. Considering two coils having turns N1, N2, which are magnetically coupled, means same flux is passing for both coils. Now, coil 1 is excited with a alternating voltage signal V1 having frequency F. Now, a current will flow in this I1. Let a current I1 is flowing. Now, due to this current I1, a flux will produce. By applying right hand thumb rule, this is the flux direction. Okay, flux is passing in this direction. The same flux will pass throughout the coil because flux will fetch for closed path. So this is the path of flux. Okay, this is path of flux. Now due to this flux, what happened now? EMF induced in both windings. Let EMF induced in coil 1 is E1 and coil 2 is E2. Now what Lenz law will say? The EMF induced in the winding or effect oppose the cause. What is the effect here? EMF induced finally. And what is the cause for this? What is cause? Flux is the cause. But what is the cause for flux again? Current. And what is the cause for this current here? Voltage signal. So finally, effect is EMF in the windings. Cause for this EMF is voltage supply. So how it will oppose is, see, the EMF induced in the windings will cause a current. And how it will cause a current? Suppose secondary side here, it is open now. Now let's connect a load here. Connect some load or just closed. Closed path is provided so that current will flow. So once it is closed, winding is closed, then current can flow. Whenever there is a voltage or EMF, current can flow in this. How that current will flow? That is important in this. So according to Lenz law, the EMF induced in the winding will cause a current. Now a current will flow in secondary winding here. And how that current will flow? That current will flow such that it will produce a flux. That flux is opposite to the main flux, which is the cause for EMF. So listen carefully. It states that the EMF induced in the windings will cause a current in such a direction. It will produce a flux. It will produce a flux. That flux is opposite to the main flux, which is the cause for EMF. What is the main flux? This phi is the main flux here. Due to this only, no, EMF induced. Now, as some load is connected or closed path is provided, current will flow. Now, can you put directly some direction of current? No, you cannot put, because current direction automatically it will flow. How it will flow? It has to produce a flux opposite to main flux. So main flux is flowing in this direction. Observe in the arrow, this is blue one. This is our main flux direction. Now, this E2 will cause a current. It has to produce a flux opposite to main flux like this. This is the flux due to EMF. And in order to produce flux in this direction, what should be the direction of current? You apply your right hand thumb rule here. Apply your right hand thumb rule. Flux direction is thumb. Considering thumb is flux direction. Now my four fingers is current direction. So you apply in your paper, you will get the exact current direction. So if you apply, my four fingers going inside, coming outside. With respect to me, it is going inside and coming outside. Then, so if I apply here, this is the direction of current I am getting. So you apply right hand thumb rule in your figure. This is current direction. So a current is flowing in the secondary winding or second coil. How that current is flowing? It is flowing in such a direction, the flux is produced due to this current is opposite to main flux, which is the cause for EMF. Okay. So directly EMF will not oppose voltage. Directly EMF cannot oppose voltage. How it is opposing? This EMF is causing a current. That current is producing a flux, and that flux is opposite to the main flux, which is the cause for everything. Okay. So this dotted blue line is what? Main flux. and this black line is, this is also flux line. Which flux it is? This is flux due to this current I2. Now it is satisfying Lenz law. So what is Lenz law? According to Lenz law, the EMF induced in the windings will cause a current in such a direction to produce a flux which is opposite to main flux. Okay. Now based on this Lenz law only, dot convention will depend. Dot, how to place dots in windings, transformer, primary side, secondary side, depends on Lenz law only. Okay. So write the statement of this. It states that the EMF induced in the windings, will cause a current in such a direction to produce a flux opposite to main flux, which is the cause to produce EMF, Okay. So according to Faraday's law, EMF induced. Now according to Lenz law, that EMF will cause a current in the winding such that the flux produced due to that winding current, it will be opposite to main flux. So same thing will apply to transformer figure also. Same whatever we will see here. Okay, this is Lenz law statement. EMF voltage directly will not oppose. EMF induced will not oppose directly. But how it is opposing? It is causing a current, that current producing a flux, that flux is opposite to main flux. So to satisfy that, we are considering minus sign in the magnitude of this EMF. Let's see the gate 21 question given on this calculation of mutual induced EMF. Observe this question. So this is for 2 marks. An air core radio frequency means high frequency, given 100 kilohertz here, as shown, has a primary winding and secondary winding mutual inductance M between the windings of transformer. So mutual inductance we need to calculate in microhenry. Mutual inductance we need to calculate. How to find this? Simple. Voltage signal frequency given, but how much voltage is not given directly. But observe, to the same primary winding, a resistor is connected here. To the same primary winding, a resistor is connected, and across that resistor, some voltage rating given, and that voltage is peak to peak voltage. 5 volts peak to peak means this is sinusoidal voltage. Sinusoidal, and peak to peak means this voltage is given 5 volts. Okay, generally how we write voltage signal? Vm sin omega t, sinusoidal variation, Vm sin omega t. So we need only maximum but not peak to peak voltage. Then what is the maximum voltage? 2.5 volts. Therefore the voltage across this 22 ohms is Vm sin omega t. Vm is peak voltage. What is the peak voltage? 2.5 volts. Vm it is sin omega t, sinusoidal. Okay. Then you can find current on primary winding or not. Yes. How to find? If you know voltage and resistance value, you can find current V by R. So voltage across this resistor we have 2.5 sine omega t and 22 ohms. Now what is the current equation? I1 equal to I1 primary current, I1 equal to voltage by this resistance value 2.5 sine omega t divided by 22. Calculate this. How much? 2.5 by 22. This is I1 equal to 0.1136 sine omega t. Okay. So I1 signal we got. The I1 signal we got here. But what we need to find? M we need to find. How to find M? How to find M? So if you remember, just now we have seen mutual induced EMF. What is the mutual induced EMF? E2 equal to M into di1 by dt or not? Just now we have seen this equation. So it's mutual induced EMF E2 equal to M into di1 by dt. Now M we need to calculate. Now I1 we have or not? Yes, I1 we have. I1 signal we have. And M we need to calculate if you know E2. E2 is there or not? Yes, E2 also there. Observe secondary side across the winding there is some voltage 7.3 volts peak to peak. This is also peak to peak voltage. Then what is the maximum voltage? Half of that only, no? Half of that 7.3 by 2. 7.3 by 2 volts. Okay. 7.3 by 2 volts. Now you can use this here directly. Peak voltage is 7.3 by 2 M into M value di1 by dt. D by dt of I1. What is the I1? 0.1136 sine omega t. So it will be M into what is 0.1136 sine omega t is cos omega t into omega. Calculate. 7.3 by 2. Calculate M value, mutual inductance. How much? So here directly you don't take the maximum value. First to take E2 equation, then in that you have to equate this. Yes, right. So first you take directly here E2 only. Don't substitute it is directly because it is maximum value now. So this is E2, this is E2. Okay, M into 0.1136 omega into cos omega t. And what is omega? 2 pi f. Frequency is there. F equal to how much? 100 kilohertz. So E2 equal to M into 0.1136 into omega is 2 pi f into cos omega t. So this is in instantaneous value. So it is varying with cosine function now. Now in this M into, you have to find this value how much? 0.1136 into 2 pi into EF. What is the frequency given? Same frequency. Transformer frequency will not change. Same primary side, secondary side. 100 kilohertz, 100 into 10 cube into cos omega t. So this is in sine function or cosine function, sinusoidal variation. Now in that, what is the maximum value? This is the maximum value, Vm cos omega t. This value is maximum value. Now what is the maximum value given on secondary side? 7.3 by 2 volts. Peak to peak is 7.3, and what is the maximum value in that? Half 7.3 by 2. Therefore E2 maximum from the equation is what? M into, calculate this value, how much? 0.1136 into 2 pi into 10 power 5. You have to find this 0.1136 into 2 pi into 10 power 5. So this is maximum value. Sinusoidal variation maximum value is this much. Vm cos omega t maximum is this, and this maximum is how much from the given data? 7.3 by 2 volts. Okay, now both equating, you will get m value from this. How much? Yes, very easy question, but getting idea during this is very, very important. Radians per second, but frequency given is in hertz, no? That's why directly 2 pi f you can take. Otherwise, if input side frequency given in radians per second, then you can use same radians per second directly. How much? So you get 50.9 microhenry approximately. So got it all of you same? Nearly 50.9 or 51 microhenry, right? Yes, all of you correct. So take care of that values. Somebody may take 5.1 or 51.1 or 0.51. So take care of this. So approximately 51 microhenry is correct. Exactly 50.9 something you get mutual inductance. So clear all of you this? Any doubt? So first we calculated primary current, and we have the mutual induced EMF equation is E2 equal to M di1 by dt. So once you know that I1, we differentiated, we got one equation, and from that equation maximum value we taken, because secondary side they given maximum value and both equated. So from there we are calculating mutual inductance. Okay. Lastly, right hand thumb rule, then we'll right hand thumb rule, right hand thumb or grip rule, right hand thumb or grip rule. So everyone knows it is, but still right hand thumb or grip rule. So this rule in transformer, applying this rule is very easy, but in rotating machines, particularly in the synchronous machine and induction machine, it is little carefully or difficult, means little confusions will come while applying this right hand thumb rule there. But in transformer, it is very easy to apply. So what is right hand thumb rule or grip rule? In the right hand, if the thumb indicates direction of current, then the curled fingers indicates direction of flux, and vice versa. Here we have two cases. One is a single current carrying conductor, and second case is coil. So both we will take. So write the statement first. If the right hand thumb indicates, if the right hand thumb indicates direction of current, direction of current, then the curl fingers indicates, curl fingers means the remaining four fingers, thumb indicating current, then remaining four fingers indicates flux direction around that. Then the curl fingers or forefingers indicates direction of flux, and vice versa, vice versa. Okay, so everyone knows this well, but still while applying this rule, some problems will come. Now see the two cases. So first case I am taking single current carrying conductor, single current carrying conductor. Let it is carrying a current I in this direction. Now simply hold a current carrying conductor in your grip, inside the grip. Hold a current carrying conductor inside the grip. Then the thumb indicating current direction. Around that, the curl fingers indicates flux direction. Means around this. So thumb is current direction. The four fingers around that. If you apply the four fingers, my fingers are going inside the board here and coming outside here. It is going inside and it is coming outside. So how to indicate inside and outside? Current directions or flux direction. Cross indicates going inside the board or paper. Dot indicate coming outside the paper. Fingers, four fingers going inside, coming outside, and thumb indicates flux current direction. Right hand thumb indicates current, and this red one indicates flux direction. It is. This is case one. It is simple. Now let us consider a coil. Taking an electromagnet, best example is electromagnet. So a coil is wound on this and giving a DC supply to this. Now it will act as a magnet. Now what is the direction of current here? Current plus minus. Current will flow in this direction. So current is going in this direction in the coil. Now apply right hand thumb rule. Now four fingers will become current here. However, the current is flowing in the same direction, your fingers you have to curl. Then the thumb indicates flux direction. Therefore, this is the direction of flux. So in this direction, flux will flow. Okay, this is flux direction. Now, where is the north and south polarity here? In the magnet, where is north and south? So this will act as a north pole, and this end is acting as a south pole. Flux is going outside now. From north, flux will go outside. Remember simply regarding this magnet. What is the direction of flux? North to south. North to south externally. South to north internally. Okay. North to south in the air. South to north in the iron or core. Now, how to change polarity of magnets? How to change polarity of this magnet? Suppose two methods. Yes, one is what? You simply change this is minus, this is plus. Interchange supply. Interchange supply terminals. Then north and south also will interchange. This is one method. Another method is without interchanging supply. This is a magnet, no? This is iron bar. Now you start from here. So I'm changing sense of winding here. Observe. Same supply I am giving plus minus. I am not changing supply polarities, but I changed sense of winding. Sense of winding I changed. Now observe from left to right to understand sense of winding. Left to right. This is suppose iron bar. From left to right, in the first case, I started from with respect to me, this is upward. I started winding like this. Okay. But in the second case, I started from left to right only. How to observe? Left to right. I started from back side. I started the winding direction from back side. Okay, like this. So this is different sense of winding. Now in this case, current direction. So from the back side, current is coming downwards here, and again here downwards. From back it go upward, and from uh, front side it is coming downward direction. Okay. Now if you apply right hand thumb rule, my four fingers, the thumb is coming in this direction. So flux direction is this. This is the flux direction. Okay. So like this, we can change polarity of magnets. Now here there is north pole and here there is south pole. So we can change sense of winding. We can also change the supply polarities, anyone. So this is about right hand thumb rule or grip rule. So with this, today we stop here and tomorrow we continue with the dot convention. Okay, dot convention. So how to mark dot polarities on primary and secondary windings. So we'll see tomorrow, and some questions also on dot convention we see. So with that, introduction part will complete, and then we start actual construction of transformer from there. Okay. So about speed, and speed is enough, or is it slow, or shall I increase the speed? Yes, increase the speed means maybe some people are there from last year. Okay, so I will increase, but main thing here is it should be for everyone, not for only some people. No? It should be for everyone, those who joined freshly also and who are learning from basic starting also. So that's why we are going in the little slow only. Okay, good. And those who already listened previously, just you need to little patience required. Okay, to listen some small topics again. Patience required. Any more doubts? Still, it is starting only. It will come. The deep concepts will come in the next classes. 25F. Polarity of magnet we require to change. If it is required to change EMF polarity, suppose EMF, so in generators mainly we change that, but transformer anywhere you can connect. But particularly in DC generators, if you want to change the EMF polarity, then we need to change field polarity first. Okay, here it is not required. Magnetic flux only. Jitender,
Hello.
tell me, Jitender.
Good evening, sir. Sir,
Good evening.
I have a general doubt in machines.
Tell me.
Like you did an example today,
Uh,
wherein uh, the experiment you told to do.
yes. Faraday's law.
Yes, sir. So
Uh,
in such examples,
uh,
or in any machine also,
uh,
sir, if every all the conditions are satisfied, only then the circuit will be completed and the light will glow.
yes,
If
yes,
suppose we are not closing the circuit and then also we are rotating,
yes. No use.
sir, in that case we are giving mechanical energy, but it is not getting converted into electrical energy. So
It is
sir,
converted because EMF is there in that now. Voltage is there. If you put a voltmeter or any sensing device, it will show voltage.
but what the power is not being utilized. Now
Yes,
current
yes,
is
not
zero.
utilized. Yes,
So it
yes,
is zero power. That means energy is not getting converted.
yes,
Then
yes.
where is that mechanical energy going, sir?
That is in the form of, if you see transformer also under no load condition, input you are giving, but no load means output is zero. But still it is consuming some power, no? Where it is going? In the form of losses.
But in transformer, we can say no, it is not taking also power from input. But here, mechanical we are giving. Like in machine, you can see any.
Hmm.
Then
Hmm.
that generator, let's say, we
Hmm.
are giving some input, and if it is in no load condition, then where
Yes.
is that power going? Because everything is moving, moving parts and all. But
At
still,
that time, it is in the losses, na bearing losses. bearing some losses will be there. It is consuming some power. When you give mechanical input, voltage is generated. When there is a voltage, iron loss will take place or not?
Sir, I don't know that much about generator yet, so
Okay, okay.
I'll not talk. But if suppose these conditions which are necessary to
Yes,
induce
yes.
EMF, if any one of those is taken away,
Uh,
then it will not work. The circuit will not work. But still,
yes,
we are giving mechanical energy.
yes.
Then
We are
in
giving.
that
We are
case, where
giving
it is going?
that condition we call floating conditions. But clearly you will see that is in the alternative topic. What is the use of that condition? Floating condition we call it is. Why it is if you are readily generated voltage, no. So whenever there is heavy demand of supply, immediately you can supply. Otherwise, you need to start the turbines and generating, and you need to control that voltage. Then only you need to give to loads. It will take time, no.
So until then, we are
Ah,
not actually using.
yes,
But
yes.
sir, where is that energy going? That
That is the
mechanical, that
loss
is
only. Means how much energy it will consume at that time? Very, very small energy, no. Generally,
how it will
under
consume small
load, if
energy, sir.
you take 100 kWh, under that condition, it may take some 0.5 kWh
But
in the
sir,
form of
the
bearings only.
motor is moving at the same speed, no? So how it is taking less energy? Like you are saying
Okay.
0.5 volt.
Hmm. Okay, you will understand in generator topic clearly that is. There I will tell.
Okay, sir.
Okay.
Thank you, sir.
Mobile.
Sir,
Yeah, tell me.
sir, that same circuit, sir, Faraday's law.
Tell me.
Sir, in that,
Hmm.
please open that, sir, while explaining.
Which slide?
Which, sir, that Faraday's law topic, sir, you have started.
Slide number means that is easy for me.
Go back. One more. One more. Yes, this one. That one only, sir.
Ah,
Forward.
okay.
Forward, sir.
Okay.
This one.
Hmm.
Sir, in that you have taken flux path from this corner to that corner, na, sir.
Hmm. Hmm. Hmm.
Because that flux flows through low reluctance path, right?
Hmm. Hmm. Hmm.
Sir, but we can take it from here in the middle also, no, sir. It is more or less
Okay.
than this.
Yes, we can take, but flux will prefer to flow throughout this core first, no? Suppose if it is coming here also, it may flow up to this, no? So a proper path is required for the magnetic flux. So low reluctance means generally we take in the closed path. Suppose if you take a permanent magnet also, why you are drawing the field lines like that?
It's
Okay.
normal, na, sir. What's problem in
Generally
that?
permanent magnet also north south. Then we draw the lines like this only, no?
Yes.
Then why we don't draw at the center that is like this? Because south is here.
But for this in this case, south is in the
Hmm.
between only, na, sir. For that,
No, no, no. If north is here, south is here only at that time.
if that rod is up to 1 kilometer, then it will go up to 1 kilometer
South,
and return.
yes, 1 kilometer only.
Yeah, I didn't get that point, sir. Really.
Hmm.
Because with respect to this winding, we got north, na, sir. At the end of
Yes,
that winding, it should be south.
yes,
I'm
not
thinking.
at the winding. So at the complete, it is a it will become a magnet, not then. So for
Yes,
magnet
sir.
two ends, it will go to two ends only. So don't think like this.
If we have a air gap between that, then what, sir?
Then suppose if there is any air gap, na,
Very
then at
small air
this end
gap,
only.
millimeters air gap, sir.
Then millimeter also considerable only. Shortest path, whatever is there, that end south will be.
Sir, consider the case we have 1 millimeter air gap, sir. Then the flux
Uh,
will flow from which, sir, in that at the end of first coil or at the end
uh,
of second coil,
first
south
only.
pole.
First only.
First,
Hmm.
and the flux won't flow through that
No, no, no.
second. Sir, but air is also a medium, sir, with mu r equal to 1.
Because
But
most of the flux will go here and small amount of flux will travel from other end.
okay, means it will flow, but
It will flow.
not considerable like that,
No,
sir.
no, no, no. Yes, because reluctance is very high for air gap. Generally, we neglect that.
Sir, while explain one more, sir. Sir, while
Hmm.
explaining mean length and reluctance, that
Hmm.
you have
Hmm.
explained 3 questions, and I've got one more, sir. That
Hmm.
2 boxes are connected side by side. That ones. 3 you have explained, na, sir. I want you to explain one more also, that two squares side by side or two rectangles side by side, like window, sir.
This one, first one, no?
No, sir. I understood all this,
Hmm.
but you didn't explain one more. I want that question also, sir, because I saw that in some of the papers.
Oh, where? Which question?
It's like 8, sir. Sir, please you draw 8, sir, in horizontal.
Then you
with
send
lines.
you send the image. I will send you that question. Huh?
Sir, two squares connected side by side, sir.
Two squares connected side by side.
Yeah, like
Okay.
this one only, sir, and draw in between them.
Okay.
This one, sir.
Uh,
That remove that middle line also.
okay. Completely joined. Just like three-phase core it is. Then
Yes, sir. The furthest, how should
three-phase
we
core.
mean length and all, sir? Reluctance.
Then completely we have to find. This is now it will become like a parallel circuit, no? So like this resistors. So this is one path. 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 Now, however we connect resistors, however we calculate resultant resistance, no? In the same way, resultant reluctance you have to find.
Sir, place points on that, sir. A, B,
Which
C, D, E.
this is one.
Above figure.
This path I am drawing as one reluctance. That is A. This is B. This is C. D. E. F. Now these three are in series.
Series we can.
These three are in series, and these three will become in parallel. So that like that resultant you have to find.
Okay. It is same as resistance as
resistance
only,
calculation on.
Okay, sir. Thank you.
Okay.
Sir, in 9F, sir.
In
9F.
9.
Sir, here you said transformer is called as a constant frequency device. Can you explain it again why it is called as constant?
Why it is input to output, any change in frequency of any signal? No, just signal is shifting. That's it. But the frequency
why
variation,
is the frequency not changing?
It doesn't. Integration and differentiation will not change frequency term. No.
Okay.
That's why signal just shifting, but no variations we are getting in frequency. Time period will not change. Same.
Sir, you said transformer is a static device, no, sir?
Yes.
What happens if it is not static device? What will happen, sir?
And nature itself static. So rotating transformer also we have. Which one that is?
Sir, here coils, here windings are inductive in nature, no, sir? What is the use of that inductive coils?
That nature of coils we are getting itself inductive, no? Magnetic energy.
We cannot get in capacitive.
Never. Capacitive nature is different. With two conducting plates, insulating, separating material is there, no? But here winding we are using. Nature of that coil is what inductor only.
Okay. Sir, here again, if input signal is given at 0 degrees, then output signal will come at 180 degrees, no, sir?
Yes.
What is you said time gap between them, no, sir? What is the time gap?
10 milliseconds. If it is 50 hertz, no, 180 degrees means how much? 360 means 20 milliseconds, 1 by 50. Time period. And what is for half cycle?
How did you say that for 360 degrees it is 20 milliseconds?
No. One cycle means what is the time period of this? Frequency 50 means what is the time period? 1 by f, 20 milliseconds. Now this what is the time period indicate? It is time required to complete one cycle. One cycle means 360 degrees, no?
Okay.
So then for 180 degrees, 10 milliseconds.
Okay.
Sai Charan.
Sir, today's section before Saturday class, sir. Before Saturday.
Huh? Slide number.
Sir, before Saturday's class, sir. That example, yeah, sir. This one, sir. Sir, can we assume that the square would be an input and triangular is the flux and other E2 is the output, sir?
Yes.
Sir, can you say once how do we get to this triangular one, sir?
No. So if you want current signal, so what is the relation of voltage and current in inductor? This is only no L dI by dt.
Yes, sir. LDA. Oh, yes.
Then what is the current from that? Integration of voltage signal.
Okay, sir.
Now, if you integrate step by step, you will get triangular shape. T means what? Ramp signal, no? T.
Okay, sir. Yes, sir.
So if time increase, magnitude also increase.
Yes, sir.
So for the triangular we draw, and then differentiation will give EMF.
Okay, sir. For the same
Then we are
triangular wave,
getting square.
if we differentiate.
Yes. Yes.
Sir, another doubt, sir.
Hmm.
Sir, here 180 degrees phase shift you told us, sir. Hello, sir.
Tell me.
Sir, this 180 degrees phase shift I did not understand, sir. Between input and output.
So voltage signal and these two you have to observe. Voltage signal we take in reference from zero, no, starting.
Yes, sir.
Then step by step what happened? Current 90 degree shifted because of inductive nature of winding. And flux produced in phase with current always. Okay.
Okay, sir.
Then EMF is what? Rate of change of flux. Because
Okay,
of
sir.
Faraday's law, due to the rate of change of flux, EMF lags flux by 90.
Okay, sir.
So total 180 degree shifted, no?
Okay, sir.
That's
Sir, in this mean length, if we take an unsymmetrical figures, what would be the mean length, sir?
one symmetrical.
Unsymmetrical figures, sir.
Then you have to find accordingly that distance they will give in the question, no?
Mean
It
length
is-
distance.
You have to calculate for any suppose rectangle they given. They will give what is the length of each side. There you have to find the exact average length of outer and inner.
Okay, sir.
Sir,
Yeah, tell me.
sir, for any input in a transformer, sir, for any input like square or triangle or sawtooth or any for any wave, the output will be same, no, sir. But
Same.
phase shift will be 180 degrees.
Yes.
Magnitude on everything will be magnitude.
No, magnitude may change depends on number of turns also.
If number of turns in the primary winding and secondary winding are same in both the cases, then
Then same voltages.
same voltages. If we change the number of turns, then it may
Yes.
the magnitude may change, but 180 degrees is same,
Yes.
and the shape is also same.
Yes.
Okay, thank you, sir.
Sir, in 25F, sir.
Huh?
25F.
25 Srimati.
The mean length is 8. It's a mean of 16 and 20, sir.
Yes, just average.
Okay, sir. Thank you, sir.
Okay. Mr. Vamshi. Vamshi not there. Sagarika.
Yes, sir.
Tell me.
Sir, how to find mean radians when upper and lower radius are given?
Mean
Radius.
radius. No. Suppose upper radius is 6. This is 3. Then what is 6 minus 3? 3, no?
Yes, sir.
Means total 3 centimeters. And what is half of this? 1.5, 1.5. Now 3, this is 3 plus 1.5, 4.5 centimeters.
So why 1.5?
This total 6, no? Outer radius. outer radius is given 6, inner radius is 3. Now what is distance between these two? 6 minus 3, 3 centimeters. This total
Okay.
length 3, and what is half of that exact center? 1.5, no?
Okay, sir.
3 plus 1.5. Okay,
One skip 20F
20.
20F slide. Okay, sir, finish.
Okay, right. Pratyush.
Sir,
Hmm.
sir, that M we have taken as a mutual inductance. Sir, that M12 or M21, how to decide, sir? How what it indicates?
Yeah,
Define
M12
M12 means
means
what, sir?
M12 means primary to secondary when you give supply to primary side.
When we give
Supply to
supply
primary
to
side.
primary,
M21 means when you
EMF
give supply to
induced.
secondary side.
M12 means supply is given to primary and EMF induced in second.
Yes, yes, yes,
M21 means supply is given to secondary, EMF
yes,
induced in one.
yes.
Okay, M
So, Vinita. Tulasi.
Hello, sir.
Tell me, Tulasi.
Sir, in 15F, sir.
Hmm.
Sir, their relative space variation means what, sir? I mean, particularly about space.
Relative space variation, we have two things, mainly conductor and flux. First of all, flux in that is time invariant, means constant flux or DC flux.
Okay, sir.
Now, in that case, anything may vary. Maybe flux is rotating, conductor is stationary, or conductor is rotating, or flux is stationary. Anything. So, if you take DC generator, no. In that, which one is rotating? Flux or conductor?
Conductor.
Armature is rotating, flux is stationary. That is also dynamical induced EMF. And if you take synchronous generator, which one is rotating there?
Field.
Flux is rotating, rotor.
Yes, sir.
That is also space variation, dynamical induced EMF.
Okay, sir. Sir, in 25, sir. Sir, here you explained about that small a, sir. For square, first question.
Area of square.
Yes, sir. I didn't get that one.
This is cross section I'm talking. So this is square core. No, square means shape is square, and this part, this is called limb. Tomorrow classes you will get it clearly that. So this part, if you cut here, and take that piece outside, it will be like this only, no?
Yes, sir.
4 sides. Then each side length is A. Then what is the area of this? A square.
For only that is a small part, no, sir.
Cross sectional area only now we required.
Okay.
Cross
Total
section.
area.
Cross section.
Okay, sir.
Wherever you place winding, that cross section required.
Okay. Thank you. That's
Abdul Rahman.
Hello, sir.
Tell me.
Sir, I want to explain. You want to explain again? Constant power device transformer is here.
Constant power, because what is the primary voltage current product and secondary voltage current product in transformers always same.
Okay.
It won't change. How it is coming, I will show you in operation of transformer again. Okay.
Okay. Sir.
All your doubts will be
Thank
cleared
you,
in the next coming classes.
Thank you.
Akash.
Sir, once again, will you explain that problem of calculating mutual inductance? Due to signal problem, I can't get it, sir.
This one.
Yes, sir.
So here primary side, in series with winding, one resistor is connected, and across the resistor voltage given. That voltage is peak to peak voltage, means like this 5 volts. Then what is the maximum voltage? 2.5 only, no?
Yes, sir.
So for that reason, the voltage across the 22 is Vm sine omega t. In this form, I'm writing Vm sine omega t.
PM, sir.
Vm means 2.5 only.
Yes.
Sine omega t. Then what is the current here? Current I1 is voltage by resistor. That is it.
Okay, sir.
And that apply mutual induced EMF.
Thank you, sir.
Jai Devidas. Yugasri.
రేడియాస్ ఉంది కదా సార్ ప్రాబ్లం ఇంతకు ముందు చెప్పారు.
Which one?
సర్కిల్ రేడియస్ తీసుకున్నారు కదా సార్ ప్రాబ్లం ఒకటి.
30 radians. ఎక్కడది?
సర్కిల్ ఒకటి ఉంది చూపించారు 5 రేడియన్స్.
Slide number.
రిలక్టెన్స్ లో సార్ ఎగ్జాంపుల్ చెప్పారు కదా సార్.
ఇదేనా?
ఇదే సార్. సార్ 6 సెంటీమీటర్స్ రేడియన్స్ ఉన్నప్పుడు 3 అన్నప్పుడు అక్కడ 4.5 సార్ 5 సెంటీమీటర్స్.
4.5 వస్తుంది. This is 6. Okay. This is 3. Now what is this mean radius? This is 6. This is 3. Means this total is how much? 3 centimeters. And in that exactly middle center we have to take. That is 1.5. No.
Yes, sir.
So 3 here and this is 1.5. Total 4.5.
Yes, sir.
That is mean radius. Then we can calculate this length 2 pi r.
You taken 5 as a radius there. That's why why you taken 5, sir? I did not understand.
This is just example I given. Let 5 centimeter, for example. Directly I given first, and this is one model, and what other model is like this. They may give 6, 3 here. Okay, just example. First I given 5, then other example like this I given.
Okay, sir. Okay. And the last example you taken, sir?
Mutual inductance, no?
Yes, sir.
Problem.
Yes, sir. Problem.
Oh, this one.
Here cos omega t, what you taken, sir? There.
Cos omega t?
Value, what is you taken, sir?
This is E2 only. Then what is the maximum old EMF of this? Maximum when we get, when cos is 1, no? So this is E2, m some value into cos omega t. What is the maximum of this E2? Whenever cosine is 1, what is the maximum of sine or cosine? 1. That's why taken this is 1 maximum value. This is generally E2 equal to like in the form of Vm cos omega t it is. What is Vm? This value. Okay. And this is given in the question. Vm is 7.3/2. That is I equated both.
10 square is added, no, sir. That's why I can't understand.
Which one? Which one?
The cos omega place, you taken 10 square. That's why only, no, sir. 10 power 5 came.
10 square.
Okay, I understood, sir.
100 into
Okay,
10 cube.
100 into 10 power 3. Okay, I understood.
Okay.
Hello, sir.
Yeah. Who is this? Mukul.
Mukul.
Tell me.
Sir, what is the difference between instrument transformer and power transformer?
Instrument
transformer, like current transformer or potential transformer.
So they are designed for small current ratings, like the protection purpose only. Instrument transformer and voltage transformer.
Okay.
So instrument transformer.
So sir, working is it working
Same, working is same, but power current ratings will be very different. Like 1 ampere, 5 amperes, it will be designed.
Okay. And sir, whatever the transformer in our home appliances, like pole mounted transformer.
Yes.
Sir, in that, what are that? I mean, above that transformer, there are so many components, no? So I want to know what are those components. I mean, why they are mounted on that above that transformer? Like,
Not understand. Actually, that pole mounted or whatever, these are all small rating transformers, small power rating.
okay.
In the rural supply areas, we no need a big transformer sizes. Small for maintenance purpose, they use a small power transformer. So like pole mounted transformer, small capacities.
Distribution transformer.
You can refer in Google the images. Operation working is same for any transformer, that is. Based on application, we use these different models.
Okay. And sir, why we are not using transformer in HVDC line?
HVDC line, that is DC transmission completely.
Okay. So that's why we are not.
Rectifiers only we use there directly.
Okay.
Ayyappan.
Sir, how to calculate in the square transformer areas?
Square?
Transformer area.
How
to calculate? Next.
You are from Tamil Nadu?
Yes, sir.
Page. This one.
This one.
Circular core. This is circular core, second one. Though circular core means area of circle. This is square core. Shape also square. Cross section also square.
Okay, sir.
Then each side is having, suppose area is some a, small a. Then all sides will be same, no? Then what is area of square? Side square.
Okay.
Formula, directly formula applied.
A square, the area will be, and the value A value will be how to taken, sir?
They will give A they should give, otherwise how can we calculate?
Okay.
They
Sir,
will give each side having some 2 centimeters or 3 centimeters, then we will substitute here.
Okay. So the middle of the flux area of the. Again, the circular core L is equal to 2 by R, sir.
This is perimeter formula, no? It is also perimeter of circle.
Okay, sir. Okay, so the R value will be how to taken, sir?
They will, if they given R directly, you can substitute. Otherwise, if they give like outer circle radius, inner circle radius, then 4.5. Example.
Okay, sir. Then in the reluctance formula, L by mu A.
Same formula. L is 2 by R, area is pi R square.
R square means
R is cross section radius. Small r is cross section radius. It is different, and this mean radius is different. Mean radius is for length calculation. This is cross section radius is for area calculation.
Okay, sir. Okay. This R will be small circular flux bus area, sir. Circle.
Which are small or capital?
Okay, sir. Okay. Thanks.
Okay, I'm leaving the session today. Tomorrow we meet at the same time.
Sir, hello, sir.
Vaishnavi, tell me.
Sir, in 34H, sir. Sir, in this, E2 should be 7.3 by 2 into omega cos omega t, no, sir?
No, it is given here 7.3 peak to peak voltage.
Yes, sir.
Then what is maximum voltage? Half of that only, no?
అంటే E2 అనేది మామూలుగా d by dt of 5 కదా సార్. ఇక్కడ మనకి కరెంట్ ఇస్ డైరెక్ట్లీ ప్రపోర్షన్ టు 5 కదా సార్. అప్పుడు ఇక్కడ sin omega t అనే టర్మ్ రాదా సార్?
No, ఇక్కడ మనం డైరెక్ట్ డిఫరెన్షియేట్ చేస్తున్నాం కదా. That current only we are differentiating directly. That we are getting the value directly here.
Here we are getting, sir, but E2 means d5 by dt, no, sir?
d5 by dt in terms of number of turns, n2 d5 by dt. E2 equal to two formulas. One is in terms of n2 d5 by dt, or in terms of mutual inductance, this is. That's why I said if there is a current, use this equation. If there is flux, use this equation. Okay.
Hello, sir.
Tell
Hello,
me.
sir.
Ajay.
Sir, I just want to request that if you are going to upload the video and current slide, please tell the management staff to upload it early as possible so that I can revise at least 5-6 hours before the previous lecture, next lecture.
Mostly by today night itself it will be uploaded, or by tomorrow early morning, most probably.
Okay,
Not
sir.
more
Thank
than
you, sir.
Okay.
Hello, sir.
Tell me.
Sir, can you please open the slides 3 for I want to take some screenshots, sir. 3, sir, 3. I see. 6, sir, 6x, sir, 6f, sir.
So PDF will be uploaded, no problem. You can check.
7f, sir.
Okay, PDF will be available by today night itself. You can see it.
Okay, sir.
Sir,
Huh?
sir, can you take the morning hour now, sir?
Because it is throughout India, no?
Okay.
So many people are there, that's why.
Okay, sir.
Are you completed?
We are getting problems, sir, because of that. We are asking morning hour.
If possible, we will see that. Are you completed or studying?
Completed, sir, recently.
Okay, okay.
Sir, one last doubt, sir. Sir, when the transformer when the distribution transformer fails, and if you want to install a new one, does it take some time to magnetize, sir? Will there be a
for transformer, nothing is required. Immediately you can replace. Only for alternators for parallel operation it is required.
no, sir, I'm saying that after placing it, will it take time to magnetize or what?
No time. Just in fraction of second it will be.
It will give it will be there will be
immediately, just like power cut off and power coming.
Okay, sir.
Like that. Okay, good night. Take care.